Consider the view from the shoreline. The ocean appears simple, flat, and familiar, a horizon of blue that seems well within the reach of human understanding. It is not. When we stand at the edge of the sea, we are looking at the surface of the largest, least understood environment on our planet, and the first step in understanding it is to accept how completely it has deceived us. To say the ocean is unknown is to speak a profound truth, but this word holds specific and distinct meanings within the rigorous halls of the scientific community. It is not merely a poetic expression of mystery, nor is it a simple acknowledgement of our limitations. In oceanography, the concept of the unknown is carefully categorized into three distinct realms of ignorance: the unmapped, the unsampled, and the unstudied. The unmapped refers to the physical shape of the seafloor itself. It is the topography of abyssal plains, deep trenches, and towering seamounts that have never been touched by the sound waves of our sonar instruments. We know more about the craters of the moon than we do about the contours of our own ocean floor. The unsampled refers to the vast, three-dimensional water column above that floor. These are massive volumes of fluid space, dark and cold, where no instrument has ever taken a direct measurement of temperature, salinity, or chemical composition. We can only guess at the specific conditions that exist in millions of cubic kilometers of seawater. The unstudied encompasses the biological phenomena that occur within this immense, dark space. It includes the millions of species that may exist without our knowledge, living out their life cycles in complete obscurity. It encompasses the complex interactions of marine snow, the predatory tactics of deep-sea hunters, and the behavioral patterns of life that have never been witnessed by human eyes or recorded by human technology. When we consider the unmapped aspect of the ocean, the statistics are both humbling and startling to comprehend. As of recent scientific assessments, less than 25% of the global seafloor has been mapped at what we might call house-scale resolution. This means that for more than 3/4 of the planet's underwater surface, we have no detailed topographic data whatsoever. Imagine looking at a map of the Earth where you can only see the largest mountain ranges and the broadest valleys, but every other detail is a smooth, featureless blur. This is the current state of our knowledge regarding the bottom of the ocean. The Nippon Foundation and GEBCO, the General Bathymetric Chart of the Oceans, have formed a crucial partnership to address this massive gap in our understanding. This ambitious partnership is known as the Seabed 2030 Initiative. The Seabed 2030 project is an international, collaborative effort striving to bring together all available bathymetric data from around the globe. Their ultimate, monumental goal is to produce a definitive, publicly accessible map of the entire world's ocean floor by the year 2030. It is an undertaking that requires the cooperation of dedicated research vessels, commercial shipping fleets, and advanced autonomous underwater drones. Until this project reaches its completion, our primary view of the global seafloor comes from a technology known as satellite gravity altimetry. This is a remarkable method of observation, but it comes with significant limitations that leave much of the deep ocean shrouded in mystery. Satellite gravity altimetry measures the slight, almost imperceptible variations in the gravitational pull of the Earth. These variations are caused by the enormous mass of underwater mountains, known as seamounts, and the vast absence of mass in deep ocean trenches. Because rock is denser than water, a massive underwater mountain exerts a slightly stronger gravitational pull than the surrounding ocean. This tiny increase in gravity literally pulls water toward the seamount, causing the surface of the ocean to bulge upward very slightly. Conversely, a deep trench creates a slight depression on the sea surface. Satellites orbiting the Earth use sensitive radar to measure these minute differences in the height of the sea surface, mapping the gravity of the ocean to infer the shape of the floor below. However, because water is a fluid, it spreads out the gravitational signal, meaning this method only provides a spatial resolution of about 5 to 10 kilometers. It gives us the broad, sweeping outlines of the massive tectonic ridges and the deepest abyssal plains. It does not give us anything finer than that 5 to 10 kilometer scale. A ship or a deep-sea submarine could easily collide with an unmapped seamount rising thousands of meters from the seafloor. This is simply because the peak of the mountain is too narrow to create a broad enough gravitational signal to be detected by the wide brush of satellite altimetry. Thus, the ocean floor remains a landscape of hidden jagged peaks and deep, unseen valleys. Let us take a moment to consider the sheer, staggering physical scale of the ocean itself. It covers approximately 361 million square kilometers of the Earth's surface. This is a number so large that it defies easy visualization, representing a vast, continuous expanse of blue that dominates the face of our planet. But surface area is only a two-dimensional measurement, a flat plane that tells only a fraction of the ocean's true story. The absolute magnitude of the ocean is found in its profound depth and its incredible, crushing volume. The average depth of the global ocean is 3,688 meters. That is nearly 4 kilometers of water pressing down, layer upon dense layer, sinking away from the light and into the absolute dark. The total volume of the ocean is estimated to be 1.335 billion cubic kilometers. To put this immense, almost incomprehensible figure into perspective, we must look at the space available for life on our planet. 97% of the habitable space on Earth, measured by sheer volume, is located within the ocean. It is a three-dimensional living space so immense that all terrestrial ecosystems combined represent only a tiny, fragile fraction of the biosphere. Every forest, every desert, every mountain range on land is merely a sliver of the space available to life. The vast majority of life on Earth lives suspended in this liquid void, far removed from the boundaries of solid ground and the warmth of the sun. As we descend through the water column, moving away from the sunlit surface layers, we enter a completely different, alien world. We pass into the mesopelagic zone, an area often and aptly referred to as the twilight zone. This enigmatic region spans from 200 to 1,000 meters beneath the surface of the waves. It is a world where the brilliant, life-giving sunlight of the surface rapidly fades into an absolute, cold, inky darkness. The pressure here is intense, squeezing down with the weight of hundreds of meters of water above. The temperature in the mesopelagic zone drops significantly, creating a cold, dense, and slow-moving environment. Yet, despite the numbing cold, the crushing pressure, and the fading light, this zone is not a barren or empty wasteland. It is, in fact, one of the most critical and biologically active environments on the entire planet. The mesopelagic zone is the beating heart, the biological engine room, of the biological carbon pump. This is a fundamental planetary-scale process that actively regulates the Earth's climate and maintains the delicate balance of our atmosphere. The biological carbon pump is driven by the relentless movement, the feeding, and the metabolism of countless unseen organisms. Every single night, the mesopelagic zone becomes the stage for the largest daily animal migration on Earth. This spectacular phenomenon is known to science as diel vertical migration. As the sun sets and darkness falls over the surface of the ocean, a remarkable, synchronized upward journey begins. Billions upon billions of deep-sea creatures rise from the depths toward the surface waters in a massive, living wave. They make this arduous journey to feed on the abundant plankton that bloom under the protective cover of darkness. They do this to take advantage of the nutrient-rich surface waters while carefully avoiding the sharp eyes of visual predators during the bright daylight hours. Before the sun rises again and illuminates the dangerous surface waters, these vast swarms of life turn back. They descend rapidly, sinking back into the safety and the cold obscurity of the dark twilight zone. This immense rhythmic vertical commute is undertaken by an astonishing, almost unimaginable array of diverse life forms. Among the most numerous of these daily migrants are the myctophid lanternfish. These small, fragile-looking, heavily scaled fish possess intricate light-producing organs arranged in specific patterns along their bellies. They use these glowing lights for camouflage against the faint, downwelling light from the surface, a masterful strategy known as counter-illumination. They also use their bioluminescence for complex communication within their massive, swirling shoals, and perhaps to confuse or blind potential predators in the dark. Siphonophores, which are fragile, complex, and highly venomous colonial organisms distantly related to jellyfish, also participate in this massive daily journey. Some of these siphonophores can stretch for dozens of meters, drifting through the deep water column like invisible, living, pulsing nets. Copepods, tiny crustaceans that are arguably the most abundant multicellular animals on the planet, make up a massive, vital portion of this migrating biomass. These microscopic creatures use large, feathery antennae to sense the minute vibrations of their surroundings and swim upward through the heavy water. The migration of these countless, tireless organisms is not just a fascinating biological curiosity of the deep. It is a deeply critical, entirely essential component of the global carbon cycle that keeps our planet habitable and stable. When these animals feed at the surface at night, they consume vast, incalculable quantities of phytoplankton. These tiny marine plants have already absorbed carbon dioxide from the atmosphere through the process of photosynthesis during the sunlit day. When the animals return to the depths at the approach of dawn, they transport this consumed carbon with them, locked within their bodies. They carry the carbon deep into the mesopelagic zone, far away from the surface and the open atmosphere. They release this carbon through their own respiration, breathing out dissolved carbon dioxide directly into the deep, cold, slow-moving water. They also excrete dense waste products, often referred to as marine snow, that sink even deeper into the abyssal ocean, falling like a gentle, perpetual blizzard. This entire relentless process, the biological carbon pump, moves massive amounts of carbon every single year without fail. It transfers an estimated 5 to 12 billion tons of carbon from the surface ocean to the deep ocean annually. Without this continuous biological conveyor belt constantly pulling carbon downward, atmospheric carbon dioxide levels would be significantly higher than they are today. The Earth's climate would be vastly different, far warmer, and potentially hostile to life as we currently know it. The mesopelagic zone therefore serves as a massive, critical carbon sink for our entire planet. It sequesters carbon away from the atmosphere, trapping it in the deep ocean for centuries or even millennia, locked in the cold dark. The sheer volume of living tissue required to move this much carbon is incredibly difficult for scientists to accurately quantify. In fact, one of the greatest, most enduring mysteries of the modern ocean involves calculating the true biomass of the twilight zone. For many decades, scientific estimates of this biomass were based almost entirely on physical net trawls dragged blindly through the deep water. However, it has become increasingly and undeniably clear that many mesopelagic organisms are incredibly adept at sensing and avoiding these slow-moving nets. More recent acoustic surveys, which bounce sound waves off the swim bladders of fish and the dense bodies of other creatures, suggest a completely different reality. These acoustic surveys indicate that the amount of life in this zone is far, far greater than previously believed or measured. The discrepancy between the old physical net data and the new acoustic data is not a minor adjustment in the numbers. Scientists currently disagree by an entire order of magnitude on how much life actually exists in the mesopelagic zone, meaning there could be 10 times more biomass swimming, drifting, and pulsing in the dark than our previous models had ever accounted for. This massive uncertainty is a humbling reminder of our fundamental ignorance regarding the most expansive habitat on Earth. To miscalculate the living mass of the ocean by a factor of 10 is to fundamentally misunderstand the ecological balance of the planet. Consider the implications of this staggering realization. If the twilight zone holds 10 times the biomass we once thought, it means the biological carbon pump is far more robust, complex, and delicate than our climate models currently reflect. It means that an unfathomable number of organisms are actively participating in the continuous transfer of carbon, regulating the atmosphere we breathe with every movement they make. The uncertainty stems from the very nature of the ocean itself, a fluid environment that fiercely resists our attempts to measure and catalog its contents. When a research vessel lowers a trawl net into the abyss, it creates a pressure wave, a subtle physical disturbance that precedes the net through the water. Many deep-sea organisms evolved over millions of years to detect the faint movements of predators in absolute darkness, easily sense this pressure wave and effortlessly dart away, escaping the slow, clumsy sweep of human technology. Acoustic backscatter, the technology that revealed this hidden abundance, operates on a completely different principle. It sends pulses of sound down into the deep, listening for the echoes that bounce back when the sound waves strike objects in the water. Swim bladders, the gas-filled organs that many fish use to maintain buoyancy, are particularly reflective to these sound waves, creating a strong, distinct acoustic signature. When scientists first began using sonar during the mid-20th century, they noticed a strange, continuous layer of sound-reflecting material suspended deep in the water column. This layer was so dense and so expansive that it was initially mistaken for a false bottom, a phantom seafloor that seemed to rise toward the surface at night and sink away during the day. This phenomenon, which came to be known as the deep scattering layer, was the first hint of the massive biological presence in the mesopelagic zone. We now understand that the deep scattering layer is composed of billions of migrating organisms, a solid wall of life moving in synchronized rhythm with the setting and rising of the sun. Yet, even with advanced acoustic surveys, quantifying this life remains an incredibly complex challenge. Sound waves do not distinguish between a large fish and a dense cluster of smaller organisms, nor do they accurately reflect creatures without swim bladders, such as squid or certain species of gelatinous zooplankton. Therefore, even our highest estimates, derived from the most sophisticated acoustic technology, may still be missing vast segments of the deep-sea population. The more we attempt to peer into the darkness, the more we realize how deeply the ocean conceals its true nature. This brings us back to the fundamental concept of the unknown, the unsampled, and the unstudied. Every time a remotely operated vehicle, or ROV, descends into a new region of the deep ocean, it brings back images of species that have never before been seen by science. We discover delicate, bioluminescent jellyfish that pulse with hypnotic, rhythmic light, their bodies so fragile that they would disintegrate if brought to the surface. We find strange, translucent octopuses that drift like ghosts over the abyssal plains, their behaviors entirely mysterious to us. These fleeting glimpses provided by our robotic explorers are like illuminating a massive, dark cathedral with a single flickering candle. We can only see the small circle of light cast by the ROV's powerful lamps, while the vast, overwhelming majority of the space remains hidden in impenetrable shadow. The animals we manage to observe are often blinded or frightened by the intense artificial light, meaning we are rarely observing their natural, undisturbed behavior. To truly comprehend the scale of our ignorance, we must return to the sheer volume of the water column. The mesopelagic zone, massive as it is, only extends down to 1,000 meters. Below that lies the bathypelagic zone, the midnight zone, which extends down to 4,000 meters. And below that, the abyssopelagic zone, stretching down to the abyssal plains at 6,000 meters. Finally, the most extreme and inaccessible regions of the ocean are the hadalpelagic zones, the deep ocean trenches that plunge down to nearly 11,000 meters beneath the surface. Each of these descending zones represents a distinct, massive ecosystem, governed by increasing pressure, decreasing temperature, and an absolute absence of downwelling sunlight. Yet, even in the deepest, most crushing environments on Earth, life finds a way to persist and thrive. We find strange, pale amphipods scavenging in the Mariana Trench, surviving at pressures that would instantly crush a modern military submarine. We find specialized bacteria that metabolize the toxic chemicals spewing from hydrothermal vents, forming the base of entire ecosystems that do not rely on the sun for energy. These discoveries challenge our fundamental understanding of biology and the limits of where life can exist on a planetary scale. The fact that we are still discovering entirely new ecosystems, driven by completely different energy sources, underscores the profound depth of the ocean's mysteries. Every sample of deep-sea mud brought to the surface contains a multitude of microscopic life forms, nematodes and foraminifera, that represent entirely new branches on the tree of life. The genetic diversity hidden within the deep ocean is thought to far exceed that of any terrestrial environment, holding secrets to biochemistry, medicine, and evolutionary history that we have barely begun to tap. Yet, as we slowly, painstakingly map the physical contours of the seafloor and begin to catalog the biology of the water column, we must also reckon with the fragility of these unseen worlds. The biological carbon pump, the delicate balance of the twilight zone, and the ancient, slow-growing communities of the deep sea are all deeply interconnected with the health of the entire planet. The profound isolation of the deep ocean has protected it for millennia, allowing species to evolve in a stable, unchanging environment. But this isolation is ending. As human activity alters the chemistry of the atmosphere, those changes are slowly seeping down into the abyss. The ocean is absorbing vast amounts of the excess heat and carbon dioxide we produce, leading to rising temperatures, increasing acidity, and the expansion of low-oxygen dead zones. The organisms of the deep sea, adapted to a world of absolute stability, are uniquely vulnerable to these rapid, unprecedented shifts in their environment. We are fundamentally altering the chemistry and temperature of the largest habitat on Earth, before we have even mapped its surface or cataloged its inhabitants. It is a race against time, a desperate effort to understand the ocean before it is irrevocably changed. As we begin this urgent endeavor to comprehend the abyss, we find ourselves turning to a sense that is often overwhelmed in our terrestrial lives, yet utterly vital in the lightless depths of the sea: sound. To understand the profound mysteries of the ocean, we must learn to listen, tuning our instruments to the invisible waves of acoustic energy that ripple through the water. Visual observation is inherently limited in an environment where sunlight can penetrate only a few hundred meters. Beyond the reach of light, the deep sea is a realm of eternal darkness, where cameras and human eyes can only illuminate tiny, fleeting patches of the seafloor. But sound is different. In the dense medium of seawater, sound travels far more efficiently than it does through the air, carrying information over vast, unimaginable distances. It is through the medium of sound that the true scale, complexity, and sheer vibrancy of the hidden ocean begin to reveal themselves to us. The story of how we began to listen to the deep ocean is a remarkable intersection of geopolitics, military strategy, and scientific serendipity. In the mid-20th century, as the geopolitical tensions of the Cold War intensified, the United States Navy embarked on an ambitious and highly classified project to monitor the movements of Soviet submarines. This project led to the creation of the Sound Surveillance System, widely known by its acronym SOSUS. It was an unprecedented engineering marvel, consisting of extensive arrays of hydrophones, highly sensitive underwater microphones, laid across the ocean floor at strategic choke points and along continental shelves. These hydrophones were connected by thousands of miles of underwater cables to shore stations, where human analysts and early computers worked tirelessly to decipher the complex soundscapes of the ocean. The engineers who designed SOSUS took advantage of a unique physical property of the ocean known as the Sound Fixing and Ranging Channel, or the SOFAR channel. This acoustic layer exists at a depth typically between 600 and 1,200 meters, depending on the latitude and local oceanographic conditions. Within the SOFAR channel, the combination of water temperature, pressure, and salinity creates a layer of minimum sound speed. When a sound is generated within this layer, or when sound waves enter it at the correct angle, the physical properties of the water act as an acoustic waveguide, bending the sound waves back toward the center of the channel rather than allowing them to scatter toward the surface or the seafloor. This phenomenon effectively traps the acoustic energy within a horizontal layer, allowing low-frequency sounds to propagate for thousands of miles across entire ocean basins with remarkably little loss of acoustic power. For decades, the SOSUS network was a closely guarded military secret, its operators trained to identify the faint, mechanical signatures of distant submarines amidst the cacophony of the ocean. But the operators quickly realized that the ocean was not a silent void waiting to be filled by human machinery. The hydrophones captured an astonishing array of sounds that had nothing to do with submarines or ships. They heard the rumbling of distant earthquakes, the grinding of tectonic plates, the explosive roar of underwater volcanoes, and a bewildering variety of biological vocalizations. It became clear that the deep ocean was a dynamic, noisy environment, teeming with natural acoustic phenomena that scientists were entirely unaware of. When the Cold War drew to a close in the early 1990s, the military slowly began to declassify parts of the SOSUS network, granting civilian scientists access to this extraordinary acoustic window into the deep sea. The transition of SOSUS from a military tool to a scientific instrument revolutionized the field of ocean acoustics. Researchers from the National Oceanic and Atmospheric Administration, or NOAA, established the Pacific Marine Environmental Laboratory's acoustic program, dedicated to analyzing the continuous stream of data flowing from the deep-sea hydrophones. As they sifted through the vast archives of recorded sounds and monitored the live feeds, they encountered phenomena that defied immediate explanation. The ocean, it seemed, was full of acoustic mysteries, strange, powerful sounds of unknown origin that echoed across the vast expanses of the Pacific and Southern Oceans. These unidentified sounds were given simple, descriptive names by the researchers who first cataloged them. Yet they captured the imagination of the public and sparked years of intense scientific investigation. Perhaps the most famous of these acoustic mysteries was detected in the summer of 1997. It was an ultra-low frequency, extremely powerful underwater sound that swept up the frequency scale over the course of about 1 minute. The sound was so loud that it was picked up by multiple SOSUS sensors distributed across a vast area of the equatorial Pacific Ocean, sensors that were separated by more than 5,000 kilometers. The researchers at NOAA named this phenomenon the bloop. The acoustic profile of the bloop was highly unusual. It did not match the steady, mechanical rumble of a ship's engine, nor did it resemble the abrupt, sharp crack of a typical seismic event or underwater earthquake. Instead, its frequency variation and general characteristics bore a striking resemblance to a biological vocalization. The initial analysis of the bloop suggested a tantalizing, almost frightening possibility. If the sound was indeed biological in origin, the creature that produced it would have to be incredibly massive, far larger than a blue whale, the largest known animal on Earth. This theory, though considered unlikely by the researchers themselves, captured the public's imagination, leading to rampant speculation about giant, undiscovered sea monsters lurking in the unexplored depths. For several years, the true origin of the bloop remained an enigma, a testament to how little we understood about the deep ocean environment. It was a potent reminder that the abyss is vast enough to hide almost anything. However, as the NOAA acoustic monitoring network expanded and scientists gained more experience with the diverse soundscape of the polar regions, a different explanation began to emerge. By analyzing thousands of hours of acoustic data from the Antarctic coast, researchers started to recognize a pattern in the sounds produced by ice dynamics. They realized that when massive icebergs fracture, or when they scrape and grind against the rocky seafloor, they can produce immensely powerful, low-frequency acoustic signals. In 2005, a team of scientists finally concluded that the bloop was not the call of a giant marine creature, but rather the sound of an ice quake, the sudden cracking and breaking of a large iceberg as it calved from an Antarctic glacier. The sound had traveled all the way from the frigid waters of the Southern Ocean to the equatorial Pacific, carried across the globe by the remarkable efficiency of the SOFAR channel. The resolution of the bloop mystery did not diminish the awe-inspiring nature of the sound. Rather, it highlighted the staggering power of geological and glaciological forces in the ocean. And the bloop was not an isolated incident. Just 2 years later, in March of 1999, the hydrophone arrays captured another highly unusual sound. This signal lasted for about 15 seconds and was characterized by a steady, whining tone that slowly descended in frequency. It was recorded by sensors throughout the eastern equatorial Pacific. The researchers named this sound Julia. Like the bloop, the acoustic signature of Julia was initially difficult to classify, and it took time to trace its origin. Eventually, careful analysis of the signal's arrival times at different sensors allowed scientists to triangulate its source to a region in the Southern Ocean near the coast of Antarctica. The current scientific consensus is that Julia, like the bloop, was generated by the complex and powerful interactions of ice. Specifically, it is believed to be the sound of a massive iceberg running aground, its colossal weight dragging and scraping along the seabed. The sheer friction generated by millions of tons of ice grinding against the rock produced an acoustic signal so intense that it could be heard thousands of miles away. These ice-generated sounds serve as a stark reminder of the dynamic, ever-changing nature of the polar environments and the profound ways in which events in one part of the global ocean can reverberate across the entire planet. They are the acoustic signatures of a world shaped by immense, slow-moving forces. But not all the mysterious sounds recorded by NOAA can be attributed to the fracturing and grinding of ice. Since the civilian acoustic monitoring program began in August of 1991, researchers have been tracking a continuous, enigmatic signal known as upsweep. This phenomenon consists of a long series of narrow-band, upsweeping sounds, each lasting several seconds. The sounds occur in a rhythmic pattern, and the entire series can continue for hours or even days at a time. Unlike the isolated singular events of the bloop or Julia, upsweep is a persistent, ongoing feature of the Pacific Ocean's acoustic landscape. It is a sound that has been repeating for decades, yet its precise origin remains one of the ocean's enduring mysteries. The acoustic characteristics of upsweep are distinct from known biological vocalizations, and they do not match the typical signatures of icequakes or tectonic earthquakes. Furthermore, the signal exhibits a strange seasonal variation. The intensity of upsweep consistently peaks during the spring and fall seasons in the northern hemisphere, while fading during the summer and winter. The source of the sound has been roughly located to a region in the southern Pacific Ocean, an area characterized by intense submarine volcanic activity. Scientists strongly suspect that upsweep is geophonic in origin, likely related to the movement of magma or hot fluids deep within a submarine volcano or hydrothermal vent system. However, the exact physical mechanism that produces this rhythmic, sweeping sound and the reason for its peculiar seasonal fluctuations remain completely unknown. The persistence of upsweep demonstrates that the seafloor is not a dormant, static landscape, but a highly active geologic frontier. It is a place where the Earth's crust is constantly being forged and fractured, where massive amounts of heat and chemical energy are transferred from the planet's interior into the cold waters of the deep sea. The sounds we detect are just the faint echoes of these monumental geological processes. We are listening to the heartbeat of the Earth itself, a slow, powerful rhythm that plays out in the permanent darkness of the abyss, far beyond the reach of human perception. Other transient sounds recorded during the early days of the NOAA acoustic program further illustrate the vast, chaotic energy of the ocean environment. In 1997, the same year the bloop was recorded, sensors picked up a sound named slowdown. This acoustic event lasted for about 7 minutes and was characterized by a gradual decrease in frequency. Like many of these large-scale acoustic anomalies, slowdown was traced back to the Antarctic region. Scientists hypothesized that it was caused by the friction of a massive ice sheet moving slowly over land or scraping against the seafloor, generating a long, drawn-out groan of immense power. In that same eventful year, another strange signal was recorded and named train. This sound was characterized by a steady, monotonous tonal quality that bore an uncanny resemblance to the distant rumbling of a freight train. It was detected by the hydrophone arrays in the eastern equatorial Pacific. Once again, the acoustic evidence pointed southward toward the icy expanse of the Southern Ocean. The prevailing theory is that the train sound was generated by another massive iceberg grounding on the seafloor. As currents and tides pushed the immense block of ice across the rocky bottom, the friction produced a steady, continuous vibration that resonated through the water column, creating the train-like acoustic signature that was detected thousands of miles away. These geological and glaciological sounds are fascinating in their own right, but the ocean is also filled with the complex, purposeful acoustics of life. For decades, one particular biological sound haunted oceanographers and submarine operators in the Southern Ocean. It was a bizarre, rhythmic, low-frequency sound that sounded remarkably like the quacking of a duck. Submarine crews first reported hearing this strange noise in the 1960s, and for over 50 years, its origin remained completely unknown. The sound was universally referred to as the bioduck. The bioduck signal was recorded repeatedly during the austral winter and spring, echoing through the frigid waters around Antarctica. It was clearly biological in nature, given its complex structure and seasonal patterns, but no known marine animal produced a sound quite like it. The mystery of the bioduck endured until 2014, when a team of researchers from the Australian Antarctic Division finally solved the puzzle. They managed to attach acoustic recording tags to a group of Antarctic minke whales, a species known formally as Balænoptera bonarensis. As they analyzed the data from the tags, they found the definitive proof they had been searching for. The Antarctic minke whales were the source of the enigmatic bioduck calls. This discovery was a significant breakthrough, not only because it solved a 50-year-old acoustic mystery, but because it provided crucial new insights into the behavior of a poorly understood species. Prior to this discovery, scientists knew very little about the winter movements and distribution of Antarctic minke whales. The identification of their unique call allowed researchers to use decades of archived acoustic data to track the whales' migratory patterns and understand their reliance on sea ice during the harsh Antarctic winter. The resolution of the bioduck mystery is a perfect example of how much we still have to learn about biological acoustics in the ocean. Sound is the primary sense for many marine animals, particularly cetaceans like whales and dolphins. In the dark, expansive environment of the sea, where vision is limited to just a few meters, sound is essential for navigation, foraging, avoiding predators, and communicating with conspecifics. Marine mammals have evolved incredibly sophisticated acoustic abilities, producing a diverse repertoire of clicks, whistles, moans, and songs that serve complex social and ecological functions. Consider the sperm whale, the largest toothed predator on Earth. These massive creatures hunt in the deep, lightless waters of the twilight zone and the midnight zone, searching for giant squid and other deep-sea prey. To navigate and locate their food in total darkness, sperm whales rely on an extraordinary system of biological sonar, or echolocation. They produce a series of broadband acoustic clicks using a highly specialized organ in their massive heads, known as the spermaceti organ. These echolocation clicks are among the loudest biological sounds ever recorded on Earth, capable of reaching source levels of over 230 decibels. This intense acoustic energy allows the sperm whale to detect squids at distances of over a kilometer, perceiving the precise size, shape, and speed of its prey through the echoes that bounce back. The scale of acoustic communication in the ocean becomes even more astounding when we look at the great baleen whales, such as the blue whale and the fin whale. These leviathans produce low-frequency moans and pulses that are so deep they are often below the threshold of human hearing. However, these infrasonic calls are incredibly powerful, and because they are low frequency, they are perfectly suited for long-distance propagation in the deep ocean. Under the right conditions, the vocalizations of a blue whale can travel for hundreds, perhaps even thousands of kilometers, crossing entire ocean basins. This means that a blue whale singing off the coast of California could potentially be heard by another blue whale near the Aleutian Islands in Alaska. They are engaged in a slow, vast, ocean-wide conversation that we are only just beginning to comprehend. The more we listen, the more we realize that the ocean is a symphony of biological and geological activity. It is a world where sound is the defining characteristic of existence, a world where silence is rare and communication occurs on a scale that defies human intuition. The acoustic environment is critical to the survival and ecological functioning of countless marine species. From the tiny snapping shrimp in shallow reefs to the massive whales that roam the open sea. Yet, as we begin to decode these acoustic signatures, we realize that we have barely scratched the surface of the vast, intricate web of acoustic communication that binds the ocean together. Every click, every pulse, every sweeping tone is part of a language we are only just beginning to understand. It is a language of survival, of navigation, and of profound connection in the boundless dark. As we listen to this symphony, we are reminded that the ocean is not a silent abyss, but a vibrant, chattering world, pulsing with life and energy. Yet the acoustic realm is just one dimension of the ocean's immense complexity. To truly comprehend the forces that shape this underwater universe, we must turn our attention from the water column to the very foundation of the sea. We must descend to the seafloor, a place long imagined to be a barren, motionless desert of sediment and rock. For centuries, the prevailing view of the deep ocean floor was one of complete stillness and absolute deprivation. It was assumed that life here was scarce, dependent entirely on the slow, meager rain of organic detritus falling from the sunlit surface waters miles above. This perception, however, was shattered in the late 20th century, in a moment of discovery that forever altered our understanding of biology and the potential for life on Earth. In 1977, a team of scientists embarked on an expedition to the Galapagos Rift, an active volcanic ridge in the eastern Pacific Ocean. Led by researchers including Jack Corliss, Bob Ballard, and John Edman, the team was mapping the seafloor and searching for subtle temperature anomalies in the deep water. They deployed the Deep Submergence Vehicle, Alvin, a small, remarkable submarine capable of withstanding the immense pressures of the deep sea. As Alvin descended into the darkness, navigating the rugged volcanic terrain, the scientists aboard observed something completely unexpected. The water temperature, typically near freezing at these depths, began to rise sharply. Through the small acrylic viewports, the headlights of the submarine illuminated a scene that defied all known biological principles. Rising from the basaltic crust were towering chimneys of rock, belching thick, dark fluids into the surrounding ocean. These were hydrothermal vents, geological marvels where superheated water from deep within the Earth's crust erupts into the cold, deep sea. But it was not the geological structures themselves that astonished the scientists most. It was the life. Clustered around the vents, thriving in the absolute darkness and intense pressure, were dense, vibrant communities of organisms unlike anything ever seen before. The sight was surreal. Huge, pale crabs crawled over the rocks. Enormous clams and mussels lay in thick beds, their white shells stark against the dark volcanic rock. And reaching upward toward the shimmering, heated water were spectacular fields of giant tube worms, their brilliant red plumes waving in the currents like alien flowers. The discovery of these hydrothermal vent communities was a profound shock to the scientific world. It overturned the fundamental biological paradigm that all life on Earth ultimately depended on energy from the sun. Here in the abyssal depths, photosynthesis was impossible. Instead, these thriving ecosystems were driven by chemosynthesis. The energy supporting this dense biomass came not from sunlight, but from the raw chemical energy of the Earth itself. To understand this extraordinary phenomenon, we must look closer at the chemistry of the hydrothermal vents, particularly the structures known as black smokers. These formidable chimneys form where seawater seeps deep into the fractured crust at mid-ocean ridges. As the water percolates downward, it is heated by the underlying magma chamber to temperatures that can exceed 400 degrees Celsius. Under the crushing pressure of the deep ocean, the water does not boil, but becomes a superheated fluid, highly corrosive and buoyant. As this superheated fluid interacts with the surrounding crustal rock, it undergoes profound chemical changes. It strips minerals and metals from the basalt, becoming heavily enriched with iron, copper, zinc, and, crucially, hydrogen sulfide. This buoyant, mineral-laden fluid then rises rapidly back to the surface of the seafloor. When it erupts into the near-freezing ocean water, the sudden drop in temperature causes the dissolved minerals to precipitate almost instantly. The iron and sulfide form fine, dark particles that look like billowing black smoke, giving the black smokers their name. Over time, these precipitating minerals build up, forming the towering chimney structures that can grow meters tall in just a few years. The key to the biological wealth of the vent communities lies in the hydrogen sulfide carried by the vent fluids. To most animals, hydrogen sulfide is highly toxic, but in the deep sea, it is the fundamental fuel for life. The foundation of the vent ecosystem is built upon chemolithotrophic bacteria, extraordinary microorganisms capable of oxidizing hydrogen sulfide to produce organic matter. These bacteria act as the primary producers, filling the ecological role that plants play in sunlit environments. Some of these bacteria form thick, white mats over the basaltic rocks, grazing grounds for snails, limpets, and other small grazers. But the most spectacular adaptations to this extreme environment are found in the organisms that host these bacteria within their own bodies in profound symbiotic relationships. The most iconic of these is the giant tube worm, scientifically named Riftia pachyptila. Riftia pachyptila is a creature of astonishing proportions and bizarre biology. When they were discovered in 1977, they presented a profound puzzle to biologists. Growing up to 2 meters in length, these worms have a stark white, tough outer tube, from which they extend a bright red structure known as a branchial plume. This plume is highly vascularized, filled with blood that contains a unique form of hemoglobin capable of binding both oxygen and hydrogen sulfide simultaneously. What baffled early researchers, however, was the anatomy of the tube worm. Upon closer examination, it was found that Riftia pachyptila possesses no mouth, no gut, and no digestive tract of any kind. For an animal of such massive size to exist without a means of ingesting food seemed an impossibility. The solution to this anatomical mystery was formally described in 1981, revealing one of the most remarkable symbioses in nature. The interior of the tube worm is largely taken up by a specialized organ called the trophosome. This organ is packed with billions of symbiotic, sulfur-oxidizing bacteria. The tube worm uses its red plume to absorb oxygen, carbon dioxide, and hydrogen sulfide from the surrounding water, transporting these vital elements through its unique blood directly to the bacteria in the trophosome. The bacteria then use the chemical energy from the hydrogen sulfide to fix the carbon dioxide into organic molecules, which they share with their host. In return, the tube worm provides the bacteria with a safe, stable environment and a constant supply of the necessary raw materials. The tube worm, essentially, is a farming organism, cultivating a crop of bacteria within its own body to sustain itself in an environment where conventional food is non-existent. The discovery of the Galapagos rift vents and the incredible adaptations of organisms like Riftia pachyptila opened an entirely new chapter in marine biology. For decades following this discovery, scientific expeditions focused on exploring the global mid-ocean ridge system, finding hydrothermal vents and their associated biological communities in every major ocean basin. These exploration efforts revealed a stunning diversity of life, with different vent fields hosting unique assemblages of species, from the swarming blind shrimp of the mid-Atlantic ridge to the scaly-foot gastropods of the Indian Ocean. Yet, even as our understanding of black smoker ecosystems grew, the ocean still held profound secrets. In the year 2000, a team of scientists led by Deborah Kelly and her colleagues made another groundbreaking discovery on the mid-Atlantic ridge, far off the axis of the main spreading center. They found a hydrothermal field completely unlike the black smokers they had come to know. They named it the Lost City. The Lost City hydrothermal field is a landscape of eerie, ghostly beauty. Instead of dark, metallic, sulfide chimneys, the Lost City is characterized by immense pale structures made of calcium carbonate. These carbonate chimneys, some reaching up to 60 meters in height, rise from the seafloor like the spires of an ancient, forgotten cathedral. The chemistry driving the Lost City is fundamentally different from that of black smokers. The vents at the Lost City are powered by a geological process known as serpentinization. Here, seawater interacts with mantle rock called peridotite that has been exposed at the seafloor by tectonic faulting. This reaction is exothermic, generating heat, though the vent fluids are much cooler than black smokers, typically ranging from 40 to 90 degrees Celsius. More importantly, serpentinization produces fluids that are highly alkaline and extremely rich in hydrogen and methane, but virtually devoid of the hydrogen sulfide that fuels black smoker communities. The biological communities at the Lost City are accordingly different, characterized by a lower biomass but a high diversity of microscopic life. The towering carbonate spires are coated with dense biofilms of unique microbes that utilize the abundant hydrogen and methane for energy. Larger animals are present, including small snails, amphipods, and translucent worms, but they are sparse compared to the teeming masses found at typical black smokers. The significance of the Lost City extends far beyond its unique geology and biology. The distinct conditions found here have profound implications for our understanding of the origin of life itself. The alkaline hydrothermal vent hypothesis, championed by scientists like Nick Lane and Mike Russell, suggests that the very first living cells may have emerged in environments remarkably similar to the Lost City. In this scenario, the porous structure of the carbonate chimneys provides a natural labyrinth of microscopic compartments. The steep gradients between the warm, highly alkaline, hydrogen-rich vent fluids and the cool, slightly acidic, carbon dioxide-rich ancient ocean would have created a natural electrochemical gradient, a kind of geological battery. This natural proton motive force could have driven the first metabolic reactions, providing the energy necessary to combine simple molecules into complex organic compounds, eventually leading to the emergence of early cellular life. The Lost City, therefore, may not just be a unique deep-sea habitat, but a window into the primordial conditions that gave rise to biology on our planet. As we explore further into the deep ocean, we find that the seafloor is far more dynamic and chemically active than we ever imagined. Beyond the intense heat of hydrothermal vents, there are other environments where the Earth's chemical bounty sustains rich communities of life. These are the cold seeps, enigmatic regions primarily located on the continental margins, where hydrocarbon-rich fluids slowly ooze from the sediments. Cold seeps were first discovered in the 1980s in the Gulf of Mexico, and have since been found worldwide. Unlike hydrothermal vents, the fluids emerging at cold seeps are roughly the same temperature as the surrounding seawater. The key chemical drivers here are methane and hydrogen sulfide, which seep upward from deep geological reservoirs or are produced by the breakdown of organic matter buried within the thick continental sediments. In some deep, cold environments, the seeping methane becomes trapped in a crystalline lattice of water molecules, forming ice-like structures known as methane clathrates or methane hydrates. These mounds of yellow-white methane ice can sometimes be seen exposed on the seafloor, bubbling slowly as the gas escapes into the water. Like hydrothermal vents, cold seeps host extraordinary ecosystems based on chemosynthesis. The base of the food web is formed by microbes that can oxidize methane and sulfide. These microbes often exist in complex symbiotic relationships with larger animals. Vast beds of mussels are common at cold seeps, their gills harboring methane-oxidizing bacteria that provide them with nutrition. Tube worms, related to but distinct from the giant riftia of the hydrothermal vents, also flourish here, growing slowly over hundreds of years, their roots delving deep into the sediment to extract the sulfide necessary to sustain their internal bacterial symbionts. The discovery of hydrothermal vents and cold seeps has fundamentally shifted our perspective on the deep ocean. We now recognize the mid-ocean ridge system, a continuous chain of underwater mountains stretching for over 60,000 kilometers, as a vital and biologically active frontier. It is the largest continuous geological feature on Earth, a massive seam winding through all the major ocean basins. Yet, despite decades of exploration, we have mapped and investigated only a minute fraction of this immense system. Vast stretches of the mid-ocean ridges remain completely unexplored, hidden beneath kilometers of dark water. We know from the regions we have studied that these ridges are punctuated by thousands of active hydrothermal vents, each potentially hosting unique biological communities shaped by isolation and extreme conditions. We are left to wonder about the extraordinary life forms, the bizarre adaptations, and the fundamental biological secrets that are still waiting in the dark. Every new expedition reveals species never before seen by human eyes, organisms that challenge our understanding of biology and expand the boundaries of the known world. As we consider the staggering expanse of the global ridge system, we must acknowledge the profound depth of our ignorance. We can only imagine how many isolated valleys, how many towering volcanic ridges, and how many unique vent communities remain undiscovered along unexplored ridge segments we have mapped and investigated only a minute fraction of this immense system. Vast stretches of the mid-ocean ridges remain completely unexplored, hidden beneath kilometers of dark water. We know from the regions we have studied that these ridges are punctuated by thousands of active hydrothermal vents, each potentially hosting unique biological communities shaped by isolation and extreme conditions. We are left to wonder about the extraordinary life forms, the bizarre adaptations, and the fundamental biological secrets that are still waiting in the dark. Every new expedition reveals species never before seen by human eyes, organisms that challenge our understanding of biology and expand the boundaries of the known world. As we consider the staggering expanse of the global ridge system, we must acknowledge the profound depth of our ignorance. We can only imagine how many isolated valleys, how many towering volcanic ridges, and how many unique vent communities remain undiscovered along unexplored ridge segments. These undiscovered segments form a vast, interconnected labyrinth of basalt and black smokers, silently releasing superheated minerals into the crushing pressure of the abyss. The scale of this hidden mountain range defies human comprehension, stretching like a seam across the spherical surface of our planet. It is entirely possible that entirely new branches of the tree of life have evolved here, completely separate from the sun-driven ecosystems of the surface world. We stand on the precipice of discovery, knowing that the majority of this geological phenomenon has never been touched by the lights of our submersibles. The mid-ocean ridges are a testament to the Earth's inner heat, a slow, continuous tectonic engine that shapes the very floor of the ocean. Yet, the mysteries of the deep sea are not confined to the volcanic activity of the seabed. The dark, pelagic waters above these ridges hold their own incredible secrets, organisms of astonishing size and antiquity that have evaded human detection for centuries. For a long time, the scientific consensus held that the deep ocean was a barren wasteland, incapable of supporting large, complex animals. We assumed that the crushing pressure, the near-freezing temperatures, and the absolute absence of sunlight created an environment too hostile for significant life. This assumption was born of our own terrestrial bias, an inability to imagine biology operating by a different set of rules. This arrogance was systematically dismantled not by careful observation, but by accidental encounters with animals that simply were not supposed to exist. These unexpected discoveries forced a radical revision of marine biology, proving that the deep ocean is a refuge for the ancient and the bizarre. They taught us that our understanding of the ocean's biodiversity is fragile, constantly subject to upheaval when the depths yield one of their long-held inhabitants. The deep sea is a vast repository of evolutionary history, a place where time seems to slow down and ancient lineages can persist unchanged for eons. We must confront the reality that we share this planet with creatures of mythic proportions, silently patrolling the darkness below. Consider the astonishing case of the coelacanth, a creature that fundamentally altered our understanding of extinction and evolutionary persistence. For decades, paleontologists studied the fossilized remains of Latimeria chalumni, a strange lobe-finned fish that swam in ancient seas hundreds of millions of years ago. The fossil record indicated that this lineage was highly successful, diversifying into numerous forms before abruptly vanishing approximately 65 million years ago. This disappearance coincided perfectly with the mass extinction event that eliminated the non-avian dinosaurs, leading scientists to confidently declare the coelacanth extinct. It became a textbook example of a dead end in the evolutionary tree, an animal known only from the silent testimony of rocks. No one ever expected to see a living coelacanth in the modern ocean. It was an impossibility, a relic of a bygone geological era. But the ocean is vast, deep, and remarkably adept at keeping secrets from the surface world. In the winter of 1938, a young museum curator named Marjorie Courtney Latimer was routinely examining the catch of a local fishing trawler at a busy fish market in East London, South Africa. Amidst the familiar shapes of sharks and rays, she noticed a heavy, armored fish with thick, fleshy fins that moved like primitive limbs. She recognized immediately that this was an unusual find, a fish that defied easy categorization and seemed completely out of place among the standard commercial catch. Recognizing its potential importance, she arranged for the massive specimen to be transported to her museum, where she carefully preserved it and sketched its unique features. Courtney Latimer then sent her notes to the prominent South African ichthyologist J.L.B. Smith, hoping he could identify the strange, steel blue fish. When Smith finally laid eyes on the specimen, he was reportedly struck silent by shock and disbelief. He recognized the heavy scales, the lobed fins, and the distinctive tail instantly, identifying the creature as a coelacanth. It was an earth-shattering moment in biological science, the equivalent of finding a living, breathing dinosaur wandering through a modern forest. The discovery of the living coelacanth sent shockwaves through the global scientific community, proving that a massive, distinctive animal could remain completely hidden for 65 million years. This was a Lazarus taxon, a species that had seemingly risen from the dead, finding refuge in the deep, rocky underwater caves of the Indian Ocean. The mystery only deepened decades later when a second, distinct species of coelacanth, Latimeria monatoensis, was discovered in 1997. This second population was found thousands of miles away, swimming in the deep coastal waters of Indonesia, far from the original discovery site in South Africa. The existence of these two separate populations suggests a complex evolutionary history that has played out entirely in the shadows, far removed from human observation. The coelacanth teaches us a profound lesson about the nature of our oceanic knowledge, highlighting the immense difficulty of proving extinction in an environment as vast and inaccessible as the deep sea. It demonstrates that survival is possible in the stable, slow-changing environment of the deep ocean, a sanctuary where ancient biological designs can persist, while the surface world undergoes catastrophic climatic shifts. The story of the coelacanth is a humbling reminder of our own limitations as observers of the natural world. It forces us to ask what other ancient creatures, what other prehistoric survivors, might still be gliding through the unlit regions of the world ocean. If a massive armor-plated fish could evade human detection for all of recorded history, it implies that the deep sea could hide almost anything. The ocean's capacity for concealment extends far beyond ancient, slow-moving fish. Even large, highly active megafauna can remain entirely unknown to science if they inhabit the vast, open expanses of the pelagic zone. This was dramatically illustrated by the discovery of the megamouth shark, a creature of staggering size and bizarre proportions that managed to avoid human contact until the late 20th century. In 1976, a United States Navy ship, the USS AFB-14, was operating in the deep, open waters off the coast of Hawaii. As the crew hauled up one of the ship's massive sea anchors from a depth of over 4,000 feet, they discovered an enormous, strange-looking animal tangled in the deployment parachute. It was a shark, but its appearance defied all known categories of shark biology. The creature measured nearly 4.5 meters in length, featuring a bulbous, rubbery head and an extraordinarily large mouth that seemed entirely out of proportion to its soft, flabby body. The scientists who examined this accidental, unexpected catch were astounded by its bizarre morphology. They realized they had discovered not just a new species, but an entirely new family of sharks, a major branch of the evolutionary tree that had somehow remained completely invisible to modern science. They named the creature Megachasma pelagios, which translates fittingly to the giant mouth of the deep. The megamouth shark is a massive filter feeder, slowly cruising the mesopelagic zone in search of plankton and small fish. occupying a similar ecological niche to the whale shark and the basking shark. However, unlike its surface-dwelling, easily observable cousins, the megamouth spends its life in the twilight and midnight zones of the ocean, far below the typical depths of commercial fishing operations. Its massive cavernous mouth is lined with silvery, bioluminescent tissue, a specialized adaptation that scientists believe it uses to lure small prey into its jaws in the surrounding darkness. Despite its massive size, which can reach up to 5.5 meters in adult males, the megamouth shark remains a remarkably elusive animal. Since that first accidental discovery in 1976, only about 100 individual specimens have ever been recorded globally. Most of these incredibly rare encounters have been accidental catches in deep water fishing gear or tragic instances of dead individuals washing ashore. The megamouth remains a ghost of the deep, a massive, silent predator that we know almost nothing about. We do not fully understand its reproductive cycle, its migration patterns across the global ocean, or the true size of its population. Its existence highlights a profound disconnect between the actual, hidden biodiversity of the ocean and our limited, surface-biased perception of it. We are dealing with a three-dimensional environment so incredibly vast that a 5-meter shark can remain completely hidden from human civilization for millennia. The discovery of the megamouth forces us to reconsider our confidence in our marine inventories and our biological catalogs. It implies that the open ocean, the largest continuous habitat on Earth, is still fully capable of surprising us with massive, undiscovered forms of life. It is a deeply humbling realization, a stark reminder that our presence on the ocean surface gives us only the narrowest, most superficial view of the life teeming beneath the waves. The deep sea is not empty. It is merely waiting for us to develop the technology and the patience to look closer. This disconnect between reality and human perception is perfectly exemplified by the history of the giant squid, Architeuthis ducks. For centuries, the history of ocean exploration was deeply intertwined with tales of monsters and myths, stories of many-armed beasts that could drag sailing ships into the crushing abyss. Mariners spoke of the kraken, a terrifying leviathan of the deep, a creature born of fear, isolation, and the vast, unforgiving nature of the open sea. Science long dismissed these stories as hallucinations, the exaggerated folklore of sailors spending months surrounded by nothing but water. But the ocean has a profound ability to blur the line between myth and reality, hiding the truth in its dark, inaccessible depths. The legend of the kraken was ultimately rooted in a real, living animal, an invertebrate of astonishing proportions known to science as the giant squid. For hundreds of years, our entire knowledge of this massive creature was pieced together from rotting carcasses that occasionally washed ashore on remote, windswept beaches. Additional clues came from the massive, parrot-like beaks found undigested in the stomachs of sperm whales, hinting at epic battles fought far below the surface. These fragmentary, decaying remains painted a picture of an animal with eyes the size of dinner plates and massive tentacles lined with sharp, serrated suckers. Yet, despite centuries of searching and numerous scientific expeditions dedicated specifically to finding a living specimen, the giant squid remained a phantom in its natural habitat. It seemed almost impossible that an animal capable of reaching lengths of 12 meters or more could entirely evade human observation in the wild. The search for the living giant squid became one of the great defining quests of modern marine biology, a technological and scientific challenge that spanned decades of frustrated effort. It was not until the year 2004 that scientists finally achieved a monumental breakthrough in this centuries-long search. A dedicated Japanese research team, led by Tsunemi Kubodera and Kyoichi Mori, spent years meticulously tracking the diving patterns of sperm whales off the Ogasawara Islands in Japan. By deploying deep-sea camera systems baited with squid jigs in the exact, high-pressure hunting grounds of the whales, they finally captured the first photographic evidence of a living giant squid in its natural environment. The images of this massive, rust-colored creature actively attacking the bait were a triumph of persistence and technological ingenuity. 2 years later, in 2006, the same research team returned to the region and successfully captured the first video footage of a live Architeuthis ducks. They managed to pull a relatively small female specimen to the surface, observing its coloration and movements before it succumbed to the drastic changes in pressure and temperature. These monumental achievements were the result of immense effort, but they also highlighted the extreme difficulty of studying the deep ocean ecosystem. The long, frustrating history of the giant squid perfectly illustrates a fundamental problem in our study of the ocean, a critical scientific concept known as detection bias. For centuries, our entire understanding of the giant squid was based exclusively on the sick, the dying, or the dead. We only knew about the animals that were forced out of their natural deep-water habitat, either by illness, shifting ocean currents, or the violent aftermath of a sperm whale attack. We were studying the refuse of the deep sea, trying to extrapolate the complex behavior and ecology of a magnificent, active predator from its decaying remains on a beach. The healthy living animals perfectly adapted to their dark, high-pressure environment were completely invisible to us, operating in a realm we could not penetrate. Detection bias means that our biological knowledge is heavily skewed toward the animals that are easiest for us to find and observe. We know about the creatures that live in shallow coastal waters, those that frequently interact with human fishing gear, or those that occasionally wash ashore due to environmental anomalies. The vast majority of deep-sea life existing in perfect equilibrium with the extreme conditions of the abyss never crosses our path and never registers on our instruments. They live their entire lives, generation after generation, without ever being detected by human civilization. The giant squid was considered a creature of myth simply because we lacked the ability to enter its realm on its own terms and observe it in context. When we finally developed the deep-sea technology to reach into the dark, the myth dissolved into a fascinating, complex, and beautiful reality. This realization forces us to ask ourselves a profound question about the nature of oceanic discovery. We must wonder how many other myths are waiting to be proven true, and how many incredible biological realities exist that we have never even begun to imagine. As we venture deeper into the unlit layers of the ocean, the fundamental rules of biology seem to change, bending to accommodate the extreme conditions of high pressure, low temperature, and perpetual darkness. In the mesopelagic and bathypelagic zones, we encounter organisms that seem almost alien, creatures that have evolved entirely unique strategies to survive in an environment where food is incredibly scarce. The animals of the deep must optimize every movement, conserving energy while maximizing their chances of finding sustenance in the vast, empty water column. One of the most fascinating and misunderstood of these deep-sea denizens is Vampiroteuthis infernalis, scientifically known as the vampire squid from hell. Despite its terrifying dramatic name, the vampire squid is not a fearsome monster of the deep, nor is it a threat to any large animal. It is a relatively small, soft-bodied, gelatinous creature, typically measuring no more than 30 centimeters in total length. It possesses large, globular, sapphire blue eyes, which are proportionally the largest eyes of any animal on Earth, perfectly adapted to detect the faintest glimmers of bioluminescence in the dark water. The vampire squid is a fascinating evolutionary relic, a unique animal that is neither a true squid nor a true octopus, despite its superficial resemblance to both. It occupies its own entirely distinct taxonomic order, the Vampiromorphida, standing alone on a distant, ancient branch of the cephalopod evolutionary tree. It primarily inhabits the oxygen minimum zone, a specific layer of the ocean located between 600 and 900 meters deep. In this zone, oxygen levels are so incredibly low that most other complex active animals would quickly suffocate and die. The vampire squid has evolved remarkable physiological adaptations to thrive in this harsh, oxygen-deprived environment. It utilizes a uniquely efficient blood pigment, hemocyanin, which binds oxygen far more effectively than the hemoglobin found in most vertebrates, allowing it to breathe in the suffocating darkness. For decades, scientists assumed that the vampire squid, like most of its fast-moving cephalopod relatives, was an active predator, actively hunting small crustaceans and fish in the dark. Its dark red coloration, its webbed arms lined with fleshy, tooth-like spines, and its menacing scientific name all suggested a fearsome, predatory lifestyle. However, careful observation in the wild, using deep-diving remotely operated vehicles, revealed a completely different, entirely unexpected reality. The feeding strategy of the vampire squid was fundamentally misunderstood by science for nearly a century. It turns out that Vampiroteuthis infernalis is not a predator at all, but rather a slow-moving scavenger of the deep, a detritivore that feeds on the slow, continuous rain of organic debris falling from the sunlit surface far above. This debris, known as marine snow, consists of dead plankton, shed exoskeletons, fecal matter, and decaying animal parts slowly sinking into the abyss. To feed, the vampire squid deploys two long, sticky, thread-like filaments, extending them outward like delicate fishing lines in the dark, still water. These specialized filaments capture the falling marine snow, which the squid then carefully scrapes off and consumes using its arms and webbed cloak. It is a slow, remarkably energy-efficient lifestyle, perfectly suited to the oxygen-deprived, food-poor waters of the deep, mesopelagic zone. The discovery of the vampire squid's true feeding habits is a prime example of how remote and deeply mysterious the deep ocean truly is. It took decades of advanced technological development to simply observe this small animal going about its daily, unassuming life in its natural habitat. Until we could regularly send specialized camera systems down into the abyss, our assumptions about the vampire squid were based entirely on its terrifying appearance in a laboratory jar. We had imposed our own terrestrial expectations of predatory behavior onto a creature that operates by a completely different set of ecological rules. The deep ocean is full of such surprises, animals that defy our logic and challenge our fundamental understanding of marine ecology. Every time we send a remotely operated vehicle down into the dark, we risk upending decades of established scientific thought and theoretical biology. We are forced to observe the deep sea on its own terms, slowly uncovering the bizarre, elegant, and highly specialized solutions that life has found to survive in the most extreme environment on Earth. The deep sea does not conform to our expectations. It demands that we adapt our understanding to its strange, slow, and ancient rhythms. The slow pace of life in the deep ocean is not merely a consequence of the freezing temperatures and the crushing dark, it is a fundamental, essential survival strategy. In environments where resources are sparse and unpredictable, conserving energy becomes the paramount driving force of evolution. This extreme energy conservation can lead to remarkable biological adaptations, including extraordinary, almost unbelievable lifespans that challenge our understanding of vertebrate biology. In the frigid, unforgiving waters of the North Atlantic and the Arctic Ocean, we find an animal that has taken the concept of slow living to an unprecedented evolutionary extreme. The Greenland shark, Somniosus microcephalus, is a massive, incredibly sluggish predator that slowly patrols the deep, freezing waters of the northern latitudes. They are large, imposing animals, frequently comparable in size and weight to the great white shark. But they lead a completely different, almost lethargic kind of existence. They move with incredible, deliberate slowness, conserving their precious energy as they scavenge for carrion on the seafloor or attempt to ambush unwary seals in the freezing darkness. For many years, scientists strongly suspected that the Greenland shark was a very long-lived animal due to its cold environment and slow movements. They are known to grow at an incredibly slow rate, perhaps less than a single centimeter per year, and they inhabit an environment where metabolic rates are severely depressed by the extreme, near-freezing cold. However, accurately determining the exact age of any shark species is a notoriously difficult and complex task for marine biologists. Unlike bony fish, which possess calcified ear bones called otoliths that form distinct, countable annual growth rings, sharks have completely cartilaginous skeletons that do not record age in a straightforward, easily readable manner. The true, maximum age of the Greenland shark remained a frustrating mystery for decades. This mystery was finally unraveled in a groundbreaking, highly publicized study published in the prestigious journal Science in the year 2016. A dedicated team of international researchers, led by marine biologist Julius Nielsen, utilized a highly novel and innovative technique to estimate the age of these elusive deep-water animals. They turned to the science of radiocarbon dating, specifically examining the eye-lens nuclei of 28 female Greenland sharks that had been unfortunately caught as bycatch in scientific survey nets. The nucleus of the shark's eye lens is formed before the animal is even born and remains metabolically isolated for the rest of its long life. This isolated tissue preserves a perfect, undisturbed chemical record of the oceanic environment at the exact time of the shark's birth, completely sealed off from its subsequent life. By carefully analyzing the specific isotopes of carbon locked within these eye lenses, the researchers were able to estimate the ages of the individual sharks with astonishing paradigm-shifting results. The rigorous study confidently concluded that the Greenland shark is, by a significant margin, the longest-lived vertebrate known to modern science. The researchers conservatively estimated that the largest sharks in their study, massive females measuring over 5 meters in length, were at least 272 years old. Even more staggering, the maximum estimated age for these massive individuals, based on the statistical models, was an unbelievable 512 years. This means that a large Greenland shark swimming silently in the deep, freezing waters of the Arctic today could have been born during the height of the Renaissance. It could have been swimming through the dark water long before the Industrial Revolution altered the atmosphere, before the widespread exploration and mapping of the globe by European maritime powers. These animals have been silently, slowly swimming through the dark waters of the North, while entire human empires rose to prominence and fell into dust on the surface above. The discovery of the Greenland shark's extraordinary, centuries-long longevity has profound and troubling implications for our understanding of deep-water biology and conservation. It forces us to radically reconsider the vast timescales on which life operates in the cold, unlit, highly stable regions of the deep ocean. The life cycle of a Greenland shark is so incredibly drawn out that female individuals may not even reach sexual maturity until they are 150 years old. This extreme, slow pace of life makes them incredibly vulnerable to sudden environmental changes and modern human impacts, such as commercial fishing and climate change. Their populations simply cannot recover quickly from disturbances. The loss of a single adult female is the loss of centuries of slow, patient growth and survival. The Greenland shark stands as a living, breathing testament to the strange and wonderful rules of the deep sea, an environment that fosters forms of life that operate on timescales entirely alien and incomprehensible to our own fast-paced existence. They are monuments to patience, surviving in the dark through a strategy of extreme biological endurance. The fascinating, complex stories of the ancient coelacanth, the bizarre megamouth shark, the elusive giant squid, the misunderstood vampire squid, and the ancient, slowly moving Greenland shark all point toward a single, unavoidable, and deeply humbling conclusion. The scientific concept of detection bias is not merely a dry statistical artifact used by researchers. It is the fundamental, inescapable reality of our relationship with the ocean. We are fundamentally terrestrial creatures, tethered to the sunlit surface, and our view of the vast marine world is hopelessly distorted by our own physical and technological limitations. We only ever know about the animals that somehow, against the odds, cross the boundary from the deep pressure into our shallow, illuminated world. We know about the unfortunate creatures that wash ashore dead, their soft bodies ruined and deformed by the long journey to the surface and the crashing waves. We know about the animals that accidentally entangle themselves in our deep water trawling nets, pulled unwillingly and often fatally into the harsh light of day. We know about the rare, lucky few that happen to swim directly in front of the narrow, artificial beam of a submersible's headlights for a fleeting moment. But these interactions, however spectacular, are the exceptions, the extreme anomalies in the vast, continuous life of the ocean. The vast majority of deep-sea life, the countless millions of undiscovered species that form the true, complex ecosystem of the abyss, have never been detected by human instruments and likely never will be. They exist in a massive, parallel universe, a realm of total, perpetual darkness and immense, crushing pressure that covers the vast majority of our planet's solid surface. We are attempting to study and understand a massive, infinitely complex biological machine by examining only the few, loose parts that occasionally fall off and land at our feet on the beach. We construct elaborate mathematical theories about deep-sea ecology based on this fragmentary, highly biased evidence, fully aware that the next deep dive could change everything. We know that the next chance encounter with a strange, unidentifiable animal could render our current theories completely obsolete, forcing us to start again from scratch. Our understanding of marine biodiversity is a fragile, incomplete construct, constantly besieged by the overwhelming, crushing weight of the unknown deep. When we consider the sheer, mind-boggling volume of the deep ocean, the thousands of kilometers of unexplored mid-ocean ridges, the vast muddy plains of the abyss, and the plunging, terrifying depths of the ocean trenches, we must recognize our own ignorance. We must accept the fact that the species we have named, studied, and carefully cataloged are merely a tiny, highly biased sample of what actually exists in the dark water below. We are looking at the vast ocean through a tiny keyhole, marveling at the small sliver of light that penetrates the gloom. while completely ignoring the massive cavernous room that lies hidden just beyond our limited line of sight. The deep sea remains our planet's greatest frontier of profound mystery, a place where the normal terrestrial rules of biology are constantly rewritten by the extreme environment. It is a domain where the next deep-sea deployment, the next flash of a camera in the dark, could fundamentally alter our understanding of how life on Earth evolved and how it persists. As we continue to map the ocean floor with acoustic sound waves and send our mechanical proxies deeper into the freezing darkness, we are only just beginning to grasp the true terrifying scale of our ignorance. We must learn to embrace the uncertainty, the profound knowledge that the ocean is far larger, far older, and far more complex than we can currently comprehend or model. The inky shadows of the deep conceal ecosystems of unimaginable strangeness, biological communities that thrive in the complete absence of sunlight, driven by chemical forces and ancient rhythms we are only just beginning to understand. The terrifying monsters of our historical myths were merely vague hints, distorted shadows of the incredible, complex reality that actually exists below the rolling surface. We are left to wonder in silence what other ancient survivors, what other massive, unknown predators, and what other bizarre, highly specialized adaptations are waiting in the unlit, unexplored depths. The ocean stands as a vast, largely unopened repository of biological secrets, a silent, dark library of evolutionary history that we have barely even begun to read. We stand on the familiar, comforting shore, looking out at the featureless, shifting horizon, knowing that beneath the rolling waves lies a world of unending, profound mystery. It is a domain where the known and the unknown are separated only by a few thousand meters of dark, crushing water, and where the species we know are a tiny, biased sample of what actually exists. Yet, the mysteries of the deep sea are not confined to the volcanic activity of the seabed. The dark pelagic waters above these ridges hold their own incredible secrets, organisms of astonishing size and antiquity that have evaded human detection for centuries. For a long time, the scientific consensus held that the deep ocean was a barren wasteland, incapable of supporting large, complex animals. We assumed that the scarcity of food and the crushing pressure precluded the existence of anything more than simple, scavenging forms. But as our submersibles push deeper into the abyss and our scientific instruments grow ever more precise, this long-held assumption is being systematically dismantled. The deep ocean is not a barren, lifeless void, but a vibrant, hidden frontier. It is an environment teeming with existence, much of it surviving in forms and thriving in places that we once considered to be completely and fundamentally impossible for life to take hold. As we shift our focus from the dark, open water of the pelagic zone to the very foundation of the ocean floor, we uncover a reality that challenges our most basic understanding of where life can exist on this planet. The discovery of the deep biosphere represents one of the most profound and paradigm-shifting revelations in the entire history of marine science. In 1994, the scientific community was shaken when John Parks and his dedicated colleagues published a highly influential, groundbreaking paper in the journal Nature. This publication completely reshaped our view of the subsea floor environment. Through meticulous sampling and rigorous analysis, they conclusively demonstrated that microbial life does not stop at the surface of the seabed. Instead, it permeates deep marine sediments, existing hundreds of meters below the ocean floor, buried beneath millions of years of accumulated geological history. This hidden microbial world is not a sparse, struggling, or negligible presence. It is a vast, interconnected, and thriving biological system. The sheer scale of this discovery is difficult to fully comprehend. The total biomass of this deep biosphere is now estimated by researchers to rival, and perhaps even exceed, the combined weight of all life found on the sunlit surface of the Earth. Beneath the dark, freezing seabed lies an entire hidden world, a massive, silent repository of living organisms that go about their slow, steady existence entirely disconnected from the light of the sun and the changing seasons above. It is a staggering realization that the vast majority of our planet's microbial life might not be swimming in the water or growing in the soil, but buried deep within the Earth's crust, thriving in conditions of absolute darkness and immense pressure that we once confidently thought were completely sterile. Among these incredibly resilient and specialized organisms are thermophilic and piezophilic archaea. These single-celled life forms are the ultimate extremophiles, organisms that have evolved to survive and indeed require, conditions that would instantly destroy most other forms of life. They make their homes in the microscopic pores of solid rock and densely packed sediment. These microbes are capable of enduring extreme boiling temperatures near hydrothermal vents and the unimaginably crushing pressures of the deep crust. Cut off from the solar energy that drives the surface world, they utilize chemical energy, drawing sustenance directly from the surrounding minerals and the slow, steady decay of organic matter trapped in the sediment. They exist on a geological timescale, growing at an excruciatingly slow, almost imperceptible pace. Some of these deep-dwelling cells are believed to reproduce only once every few hundred or even thousand years, their metabolisms slowed to a bare, sustaining minimum. Their very existence pushes the absolute boundaries of biological possibility, proving that life is far more adaptable, versatile, and tenacious than human science ever dared to imagine. The profound implications of this vast, deep biosphere extend far beyond the boundaries of our own planet, reaching out into the cold, dark, and silent expanse of our solar system. The discovery of life thriving in the extreme, high-pressure, chemical-rich, and lightless environments beneath our ocean floor provides astrobiologists with a compelling, living analog for the search for extraterrestrial life. If fragile biological organisms can persist and flourish in the crushed, lightless rock of Earth's deep crust, utilizing chemical energy in the absence of the sun, it raises the thrilling and very real possibility that similar hardy organisms might exist in the subsurface oceans of distant icy moons. Moons like Europa, orbiting Jupiter, and Enceladus, orbiting Saturn, are known to harbor vast liquid water oceans trapped beneath incredibly thick crusts of fractured ice. The environmental conditions found deep within these alien oceans, absolute darkness, near freezing temperatures, and extreme hydrostatic pressure, are strikingly, almost perfectly similar to the deep biosphere of our own Earth. In this way, our own ocean serves as a critical proving ground, a living, breathing laboratory that strongly suggests life does not strictly require a warm, sunlit, and hospitable surface to begin or to survive over billions of years. The resilient, ancient archaea of our deep sea give us profound reason to look up at the night sky and wonder if we are truly alone in the universe, or if the icy, silent moons of the outer solar system are quietly teeming with their own hidden microbial biospheres, waiting patiently in the dark to be discovered. Yet, as we look outward into the cosmos with a sense of hope and scientific wonder, we must also look at our own ocean with a growing, undeniable sense of concern. The fundamental chemistry of the global ocean is currently changing at a rapid and unprecedented rate, driven primarily by the relentless accumulation of carbon dioxide in the Earth's atmosphere. Ocean acidification is a silent, invisible, yet highly destructive threat that is slowly and inexorably transforming the basic nature of the marine environment. Since the beginning of the industrial era, as human activity has pumped massive quantities of carbon into the air, the ocean has absorbed a significant portion of this gas. This absorption has caused the average pH of the ocean to drop from 8.2 to 8.1. While this may seem to the casual observer like a very small, almost insignificant numerical change, the pH scale is logarithmic. This drop actually represents a massive 26% increase in the overall acidity of the ocean's waters, a rapid chemical shift that has profound and immediate consequences for a wide variety of marine life. This changing, increasingly acidic chemistry poses a severe and existential challenge to calcifying organisms, which are creatures that rely on specific, delicate chemical balances in the water to successfully build and maintain their protective shells and skeletal structures. Pteropods, which are small, delicate, free-swimming marine snails often beautifully referred to as sea butterflies, are particularly and tragically vulnerable to this shifting chemistry. As the surrounding water becomes more acidic, their fragile, thin calcium carbonate shells literally begin to dissolve while the animals are still alive, leaving them defenseless, unable to swim properly, and ultimately unable to survive. Similarly, foraminifera, tiny microscopic organisms that form a crucial foundational layer of the marine food web, struggle to maintain their intricate calcium carbonate structures. The impact of this chemical alteration does not stop with these small creatures. It ripples rapidly and destructively upward through the entire ecosystem. It directly threatens the magnificent, slow-growing deep-water coral reefs, which rely on the same chemical processes to build their massive reef-building structures that provide critical, life-sustaining habitat for countless other deep-sea species. The physical structure and composition of the ocean are also shifting in other alarming, highly disruptive ways. The phenomenon known as deoxygenation is currently creating vast, continually expanding zones within the ocean where marine life simply can no longer breathe. As global atmospheric temperatures steadily rise, the surface waters of the ocean warm in response, and warmer water inherently has a lower capacity to hold dissolved oxygen. This warming process also significantly increases the thermal stratification of the water column, creating distinct, unmoving layers that prevent oxygen-rich surface waters from naturally mixing with the deeper, oxygen-depleted layers below. The direct result of this physical change is the rapid expansion of oxygen minimum zones, which are vast, mid-water regions of the ocean where oxygen levels have dropped dangerously and sometimes lethally low. The Arabian Sea currently contains one of the largest, thickest, and most intense oxygen minimum zones found anywhere in the world. In this region, the deep, mid-level waters are virtually stripped of all dissolved oxygen, creating a massive, suffocating dead zone that stretches endlessly for thousands upon thousands of square kilometers. Large active marine animals, such as fast-swimming predatory fish, sharks, and complex invertebrates, simply cannot survive in these hypoxic, suffocating waters. As the oxygen levels plummet, these animals are forced to either migrate to the crowded, shrinking margins of these zones or face certain asphyxiation. This forces a complete alteration in the natural distribution of species, disrupting predator-prey dynamics and upsetting the delicate, highly evolved balance of the entire pelagic ecosystem. The relentless, continuing expansion of these low-oxygen zones serves as a stark, undeniable reminder of the fragile interconnectivity of our planet's environmental systems, and how changes at the surface can silently devastate the unseen world below. As these broad, systemic environmental pressures continue to mount, the deep sea is simultaneously facing yet another, more direct, and potentially more destructive human intrusion. The vast abyssal plains and towering deep-sea mounts, regions once thought to be entirely safe, completely insulated from human exploitation by their sheer depth and remoteness, are now becoming the prime targets of aggressive, emerging industrial interests. Deep-sea mining has rapidly moved from the realm of speculative science fiction into a highly contested, imminent, and highly controversial reality. The vast, flat, sediment-covered expanses of the Clarion-Clipperton Zone, a massive area located in the eastern Pacific Ocean, are thickly littered with trillions of polymetallic nodules. These are dark, potato-sized rocks that have formed incredibly slowly over millions of years, and they are incredibly rich in valuable metals such as manganese, nickel, cobalt, and copper. These specific metals are increasingly, almost desperately, demanded by the rapidly growing global market for high-capacity batteries, electric vehicles, and renewable energy technologies. Similarly, the rocky, current-swept slopes of underwater seamounts are often thickly encrusted with highly valuable manganese crusts. The immense financial incentives and geopolitical pressures to harvest these deep ocean resources are growing stronger every day, but the environmental concerns raised by marine scientists are equally profound and urgent. Proposed mining operations threaten to completely destroy pristine, slow-growing, and highly vulnerable ecosystems that have remained stable and undisturbed for millions of years. The mechanical process of harvesting these nodules would physically strip the seabed of its living, biologically active upper layer, while simultaneously creating massive, choking sediment plumes that could drift for hundreds of miles, smothering delicate filter-feeding organisms and severely disrupting the fragile, interconnected food web over vast distances of the abyssal plain. The difficult, highly politicized governance of these remote international resources currently falls to the International Seabed Authority, an intergovernmental body tasked with the seemingly contradictory mandate of both organizing and controlling deep seabed mining activities, while simultaneously ensuring the effective protection of the marine environment. The challenge of effectively balancing immense, immediate economic interests and national resource demands with the long-term, critical preservation of the environment in a region that belongs to no single nation, but rather to the common heritage of mankind, is incredibly complex and fraught with conflict. The regulatory decisions and environmental guidelines established in the coming years will likely determine the ultimate fate of the largest, least understood ecosystem on Earth. We currently find ourselves facing a deeply troubling, deeply unresolved paradox. We are actively considering and rapidly preparing the legal and technological groundwork for the large-scale, highly destructive industrial extraction of resources from the seafloor before we have even achieved a basic, fundamental understanding of the countless species that actually live there. We are mapping the mineral deposits, calculating their financial value, and drawing up extraction plans in remote areas where the biological surveys are, at best, barely preliminary. It is entirely possible, and according to many leading taxonomists, highly probable, that these unprecedented mining operations will drive numerous species to complete extinction before they are ever discovered, formally named, or scientifically studied by humanity. We are, in essence, blindly walking into a vast, ancient library filled with irreplaceable genetic and biological information and proposing to clear-cut the entire structure simply for the raw, immediate value of the paper it is printed on, without ever bothering to read the books. The true, lasting wealth of the deep sea may not actually lie in the heavy metals scattered across its dark floor, but rather in the profound biological secrets held within the tissues and DNA of the strange organisms themselves. The pharmaceutical potential of the deep ocean is truly staggering, representing one of the most promising, untapped frontiers for modern medicine and biotechnology. The extreme, demanding conditions of the deep sea, the crushing pressure, the absolute lack of light, the scarce food, and the intense chemical environments have driven the evolution of highly unique biochemical pathways and completely novel compounds that simply do not exist anywhere else on Earth. A particularly striking and successful example of this massive life-saving potential was discovered in Halichandria okadai, a seemingly simple, unassuming deep-sea marine sponge. From the tissues of this specific organism, dedicated scientists were able to isolate a complex, highly active compound called halicandrin B. After many years of rigorous, intensive research, chemical modification, and careful development, a synthetic, highly effective derivative of this natural marine compound, named eribulin, was successfully created in the laboratory. In the year 2010, this groundbreaking drug, known commercially as Halaven, officially received widespread approval from the Food and Drug Administration as a targeted, highly effective treatment for patients suffering from metastatic breast cancer. A powerful, life-extending medication bringing hope to thousands of people around the world, directly originated in the dark, cold, high-pressure depths of the ocean. Similarly, the highly complex, specialized venom of predatory marine cone snails has yielded incredible medical breakthroughs. From this deadly venom, researchers developed zyconotide, a highly potent, non-addictive painkiller that is now used to treat severe chronic pain in patients who do not respond to traditional opiates. These remarkable, life-changing discoveries are just the very beginning, representing only a tiny fraction of what might be possible. The vast, overwhelming majority of deep-sea organisms remain entirely untested and completely unexamined for their potential biochemical, medical, or industrial applications. Many leading scientists, medical researchers, and marine conservationists urgently argue that the deep sea is, in reality, a vast, largely unexplored global pharmacy, filled with potential, undiscovered treatments for aggressive cancers, highly antibiotic-resistant bacteria, and debilitating neurological diseases. By threatening these delicate, ancient ecosystems with massive, physically destructive mining practices, we are essentially, and perhaps irreversibly, closing the heavy doors of this invaluable natural pharmacy before we have even had the chance to step inside, look at the shelves, and understand what cures might be waiting for us. The incredible, intricate molecular structures and complex, highly specialized biochemical compounds that have slowly evolved over millions of years of strict biological isolation are waiting patiently in the dark to be found, but they are incredibly fragile, easily and permanently lost to the sweeping, irreversible changes we are rapidly bringing to their environment. As we stand on the precipice of widespread deep-sea industrial exploitation, we must pause and carefully, thoughtfully consider exactly what we might be carelessly discarding in our relentless, short-sighted pursuit of raw materials for the next major medical breakthrough. The next cure for a currently untreatable disease could be hidden within the tissues of a fragile, unnamed sponge, clinging tenaciously to a manganese nodule in the crushing dark. And we are running the terrible risk of erasing that possibility forever before we even have the chance to recognize its existence or give it a proper scientific name. Our ability to reach into these abyssal depths, to even begin to understand the fragile environments we are so eager to exploit, is a relatively recent development in the long history of human endeavor. For most of human history, the deep ocean was an impenetrable mystery, a vast, dark void that was entirely inaccessible to our species. It was a realm of imagination and myth, populated by sea monsters and endless bottomless pits, because the physical realities of the ocean, the crushing pressure, the freezing temperatures, the absolute darkness, formed an insurmountable barrier to exploration. The journey to overcome these barriers required immense courage, ingenuity, and a relentless desire to push the boundaries of human engineering and scientific understanding. One of the most significant early milestones in this journey occurred in 1934, when two pioneers, William Beebe and Otis Barton, sealed themselves inside a small, spherical steel vessel called the bathysphere. This heavy, unpowered metal ball, barely large enough to hold two men, was suspended from a ship by a single steel cable and lowered directly into the Atlantic Ocean off the coast of Bermuda. As they descended into the darkening waters, peering through small quartz windows, Beebe and Barton became the first humans to observe deep-sea life in its natural environment. They reached a remarkable depth of 923 meters, a record that would stand for many years, and their detailed, vivid descriptions of strange, luminescent creatures swimming through the darkness captivated the public imagination and permanently changed our perception of the deep sea. Their daring dives proved that life could not only exist but thrive in the crushing pressures and absolute darkness of the ocean's twilight zone, opening up a completely new frontier for biological exploration. However, the bathysphere, dangling at the end of a long cable, was inherently limited and dangerous, and it would be several decades before technology allowed humans to truly roam the deepest parts of the ocean floor. The next monumental leap forward came in 1960 with the Trieste, a radically different type of deep-diving vessel known as a bathyscaphe. Unlike the bathysphere, the Trieste was a free-diving submersible, operating somewhat like an underwater hot air balloon, using a massive float filled with gasoline for buoyancy and iron pellets for ballast. On January 23, 1960, Swiss engineer Jacques Piccard and United States Navy Lieutenant Don Walsh piloted the Trieste into the Challenger Deep of the Mariana Trench, the deepest known point in the Earth's oceans. Their descent took nearly 5 hours, plunging through layer after layer of the water column, until they gently touched down on the soft sediment of the trench floor at an astonishing depth of 10,916 meters. For 20 minutes, they sat at the bottom of the world, peering through a single thick plexiglass window, observing flatfish and shrimp moving through the pale mud, proving unequivocally that complex life existed even at the most extreme pressures imaginable. Despite the historic triumph of the Trieste, its design was cumbersome and impractical for routine scientific research, and for many years after that record-breaking dive, deep-sea exploration progressed slowly. It was the development and systematic use of the deep submergence vehicle ALVIN, beginning in the late 1960s and 1970s, that truly revolutionized deep-sea science and ushered in the modern era of oceanographic discovery. ALVIN provided scientists with a reliable, maneuverable platform to directly observe, sample, and study the deep ocean environment over hundreds and eventually thousands of dives. In the decades that followed, the field of deep-sea exploration expanded rapidly with the introduction of remotely operated vehicles, or ROVs, and autonomous underwater vehicles, known as AUVs. ROVs, connected to a surface ship by a long tether, allowed scientists to spend unlimited hours exploring the seafloor in high definition, using robotic arms to carefully collect samples without exposing humans to the immense risks of the deep. AUVs, operating independently without a tether, could systematically map vast areas of the ocean floor and collect extensive water chemistry data, providing a much broader, more comprehensive understanding of the deep-sea environment. As our direct physical exploration of the ocean advanced, so too did our ability to monitor its complex, invisible physical properties on a global scale. One of the most important developments in modern oceanography is the Argo float program. an extraordinary international effort that has deployed a vast, silent network of robotic sensors across the world's oceans. Currently, there are over 3,900 Argo floats drifting freely through the global ocean currents, continuously collecting vital data on temperature and salinity from the surface, down to depths of 2,000 meters. These incredible devices operate autonomously, sinking into the depths, drifting with the currents for days, and then steadily rising to the surface to transmit their collected data to passing satellites before sinking again to repeat the cycle. The massive, continuous stream of data generated by the Argo program has revolutionized our understanding of the ocean's role in the global climate system. It has revealed, with unprecedented clarity and precision, the subtle, complex patterns of ocean warming, showing exactly how much heat the oceans are absorbing and how that heat is being distributed through the different layers of the water column. While Argo floats map the physical properties of the ocean, another revolutionary technology is fundamentally changing how we study its biology, revealing the presence of life without ever needing to see or capture a single organism. This remarkable technique is known as environmental DNA, or eDNA, and it relies on the simple fact that all living creatures constantly shed fragments of their genetic material into their surrounding environment. By carefully collecting small samples of seawater and sequencing the microscopic fragments of DNA suspended within them, scientists can create a detailed, comprehensive inventory of the species that have recently passed through that specific area of the ocean. This powerful tool is rapidly expanding our knowledge of deep-sea biodiversity, allowing us to detect the presence of rare, elusive, or highly mobile animals that are incredibly difficult to observe directly with submersibles or cameras. In 2020, a groundbreaking study using eDNA techniques analyzed water samples collected from the extreme depths of the Hadal Zone, far below the typical range of most known fish species. To the absolute astonishment of the scientific community, the analysis revealed clear, unambiguous genetic signatures from several species of sharks, suggesting that these apex predators may venture much deeper into the ocean's trenches than we ever previously thought possible. The ability to detect life through its invisible genetic echoes is just one part of a growing movement to create a more integrated, comprehensive understanding of the deep ocean ecosystem. The Deep Ocean Observing Strategy, or DOOS, is a massive, coordinated international effort designed to link together disparate research programs and global monitoring networks into a single unified system. By coordinating the deployment of sensors, standardization of data collection, and sharing of resources, DOOS aims to create a continuous, real-time picture of the deep ocean's physical, chemical, and biological state. This global monitoring network is essential for tracking long-term environmental changes, understanding the complex interactions between different deep-sea habitats, and identifying the areas most vulnerable to human impact and climate change. As we develop better tools to observe the deep ocean, we are continually discovering that the creatures living there have evolved their own extraordinary, highly specialized technologies for survival in the dark. Perhaps the most widespread and fascinating of these biological innovations is bioluminescence, the ability of living organisms to produce their own light through complex chemical reactions. In the sunlit world above, light is abundant, but in the twilight and midnight zones of the ocean, bioluminescence is the dominant form of communication, a silent, glowing language used by countless species. It is estimated that an astounding 76% of all macroscopic animals living in the deep ocean have the ability to produce bioluminescence, making it one of the most common ecological traits on the planet. The pioneering work of marine biologist Edith Witter has been instrumental in revealing the stunning diversity and complex functions of these living lights in the deep sea. Through carefully designed cameras that simulate bioluminescent displays, Witter has documented the countless ways that deep-sea animals use light to hunt, hide, and communicate in the endless darkness. The flashlight fish, for example, harbors colonies of glowing bacteria in special organs beneath its eyes, using this biological spotlight to illuminate its prey, communicate with other members of its school, and even confuse potential predators by rapidly blinking the light on and off. The deep-sea anglerfish uses a much more insidious strategy, dangling a glowing, bacteria-filled lure from a modified dorsal fin perfectly positioned above its massive, tooth-filled jaws. In the pitch-black environment of the midnight zone, This tiny point of light acts as an irresistible beacon for curious prey, drawing them inexorably toward the anglerfish's waiting mouth. But bioluminescence is not only used for hunting, it is also deployed as a sophisticated, highly effective defense mechanism against the countless predators that roam the deep. One of the most fascinating evolutionary strategies is known as the burglar alarm hypothesis, a desperate, brilliant tactic used by many small, vulnerable creatures when they are attacked. When caught by a predator, these animals release a brilliant, blinding flash of light, not to frighten their immediate attacker, but to illuminate them and attract the attention of a much larger secondary predator. This living distress signal effectively turns the tables on the original attacker, making them highly visible and vulnerable in the darkness, allowing the smaller prey a brief, chaotic window of opportunity to escape while their predator becomes the prey. The sheer diversity and ingenuity of bioluminescent displays highlight the incredibly complex, intricate ecological interactions that take place in environments that might initially appear barren and lifeless. The more we explore the deep ocean, the more we realize that it is not a vast, uniform desert, but a highly textured, varied landscape supporting numerous unique, localized ecosystems. One of the most surprising and beautiful discoveries in deep-sea biology has been the existence of extensive, highly complex cold-water coral gardens. Unlike their tropical shallow-water cousins, which rely on symbiotic algae for energy and require warm, sunlit waters to survive, deep-sea corals like Lophelia pertusa have adapted to thrive in near-freezing, pitch-black conditions. These remarkable organisms are entirely carnivorous, using their stinging tentacles to capture passing plankton and organic detritus carried by the deep, powerful ocean currents. Growing at depths ranging from 200 to over 1,000 meters, these cold-water corals slowly build massive, intricate three-dimensional structures that provide crucial habitat, shelter, and breeding grounds for countless other species. The growth rate of deep-sea corals is incredibly slow, often just a few millimeters per year, meaning that the large, complex reefs we find today are the result of centuries or even millennia of continuous, undisturbed growth. Some individual colonies of deep-sea corals are estimated to be over 1,000 years old, making them some of the oldest living organisms on Earth, holding within their skeletons a detailed, irreplaceable chemical record of past ocean conditions. Tragically, these ancient, fragile ecosystems are incredibly vulnerable to physical disturbance, particularly from destructive fishing practices like deep-water bottom trawling. Heavy trawl nets dragged across the seafloor can completely obliterate in a matter of minutes a coral garden that took thousands of years to grow, turning vibrant, complex habitats into flattened, lifeless rubble. The loss of these deep-sea coral reefs represents a massive, irreversible blow to ocean biodiversity, as the numerous species that rely on them for survival are left without shelter or sustenance. Even in the most barren, seemingly empty regions of the abyssal plain, unexpected oases of life can suddenly appear, driven by immense, sporadic inputs of organic matter from the surface world above. The most spectacular example of this phenomenon is the whale fall ecosystem, an incredibly complex, localized community that develops when the massive carcass of a whale sinks to the deep ocean floor. Because the abyssal plain is generally starved of nutrients, the sudden arrival of a 30-ton whale carcass represents a massive, unimaginable windfall, providing enough food to support a complex succession of different ecological communities for many decades. The first stage of a whale fall is dominated by the enrichment opportunists, a frenzied gathering of mobile scavengers, including hagfish, sleeper sharks, and swarms of tiny amphipods that rapidly strip the soft tissues from the massive bones. Once the flesh is gone, the ecosystem transitions into the sulfophilic stage, driven by the steady release of hydrogen sulfide gas produced by specialized bacteria that break down the rich lipids trapped deep within the whale's massive skeleton. This toxic, sulfur-rich environment supports a completely new community of highly specialized organisms, including massive, thick beds of brilliant red tube worms and strange, ghostly pale crabs that thrive on the chemical energy provided by the decaying bones. Perhaps the most remarkable inhabitants of the whale fall ecosystem are the Osedax boneworms, strange root-like creatures that lack a mouth, gut, or any conventional digestive system. Instead, these bizarre worms secrete powerful bone-dissolving acids to physically drill their way into the whale's skeleton. using a symbiotic relationship with specialized bacteria housed within their tissues to digest the rich fats and proteins hidden inside. The discovery of the whalefall ecosystem perfectly illustrates how deep-sea life has evolved incredibly specific, highly specialized strategies to exploit even the most temporary, unpredictable resources in an otherwise nutrient-poor environment. Understanding the vast, complex biological diversity of the deep ocean is intimately tied to our understanding of the physical shape, structure, and geological history of the seafloor itself. For a long time, the bottom of the ocean was thought to be a flat, featureless plain, a monotonous basin that merely collected the sediments slowly raining down from the continents above. This fundamental misconception was completely shattered by the groundbreaking, meticulous work of geologist and oceanographic cartographer Marie Tharp in the mid-20th century. Working in an era when women were often excluded from field research and marginalized within the scientific establishment, Tharp spent years carefully analyzing thousands of sonar depth soundings collected by ships traversing the Atlantic Ocean. Through painstaking, precise calculations and an incredible ability to visualize three-dimensional space from two-dimensional data, Tharp began to draft the first comprehensive, physiologically accurate maps of the ocean floor. Between 1952 and 1953, her detailed mapping work revealed something truly extraordinary: a massive, continuous mountain range running directly down the center of the Atlantic Ocean, far larger and more extensive than any mountain system on land. Even more significantly, Tharp's detailed profiles clearly showed a deep, V-shaped rift valley running precisely down the center of this mid-ocean ridge, a geological feature that strongly suggested the Earth's crust was actually tearing apart. When she first presented this evidence to her colleague Bruce Heezen, arguing that it supported the highly controversial theory of continental drift, he initially dismissed her findings as scientific heresy. At the time, the idea that the continents were moving was widely ridiculed by the geological establishment, and Heezen, fearing professional ruin, initially refused to accept the profound implications of Tharp's meticulous maps. However, as more data was collected and the correlation between the Rift Valley and global earthquake epicenters became undeniable, Heezen was eventually forced to accept the reality of what Tharp had discovered. Their subsequent collaboration produced a series of stunning, revolutionary maps that provided the crucial, undeniable physical evidence needed to confirm the theory of plate tectonics, fundamentally changing our understanding of the Earth's dynamic geological history. Marie Tharp's story is a powerful reminder of how individual scientific discoveries, often made against fierce resistance and deeply entrenched dogma, have progressively revealed the hidden, magnificent architecture of the ocean, stripping away our misconceptions layer by layer to expose the profound complexity that lies beneath the waves, and reminding us that every assumption we hold about this vast environment is subject to revision the moment we look closer. As the true nature of the abyss continues to defy our expectations and challenge the limits of our understanding, steadily accumulating into a picture more intricate and more remarkable than anyone imagined. The revelation that the ocean floor is a dynamic and complex landscape forces us to reconsider every assumption we have ever held about the deep. For centuries, we looked upon the ocean as an infinite expanse, a realm so vast and remote that it could absorb anything we threw into it without consequence. We imagined the abyss as a place completely isolated from the turbulent world above, a silent sanctuary untouched by human activity. Yet, as our submersibles have plunged deeper into the darkness, we have found that the profound isolation of the deep sea is little more than a comforting illusion. The surface and the abyss are intricately connected, bound together by invisible currents and the slow, relentless descent of organic and inorganic matter. In 2017, a team of researchers led by marine ecologist Alan Jamieson published a study in the journal Nature, Ecology, and Evolution that shattered our remaining illusions about the pristine nature of the deep ocean. Jamieson and his colleagues deployed free-falling landers into the Mariana and Kermadec trenches, the deepest places on our planet. They were looking for signs of life in the crushing pressures of the Hadal zone, specifically targeting small shrimp-like scavengers called amphipods. When they retrieved these tiny creatures, known to science as Hirondelia gigas, they made a discovery that was as startling as it was sobering. The tissues of these deep-sea amphipods were heavily contaminated with toxic synthetic chemicals. The researchers found extraordinarily high levels of polychlorinated biphenyls, or PCBs, and polybrominated diphenyl ethers, known as PBDEs. These chemicals were once widely used as dielectric fluids, coolants, and flame retardants before they were banned due to their severe environmental toxicity. Yet, here they were, accumulating in the bodies of scavengers living nearly 11 kilometers beneath the surface of the Pacific Ocean. The concentrations of these pollutants were not just trace amounts. They were staggering in their severity. In the Mariana Trench, the levels of PCBs in these amphipods were 50 times higher than those found in crabs surviving in heavily polluted river systems, such as the Liaohe River estuary in China. To find such intense contamination at the very bottom of the world raised a profound and deeply unsettling question. We had to ask ourselves how industrial chemicals manufactured in the 20th century had made their way into the most remote ecosystem on Earth, bypassing thousands of meters of water to reach the Hadal zone. The answer lies in the biological pump, a continuous rain of organic material that falls from the sunlit surface down into the crushing depths. When plastic debris and chemical pollutants enter the ocean, they do not simply float forever or dissolve harmlessly into the water column. They degrade into smaller particles, attaching themselves to sinking organic matter, dead phytoplankton, and the descending carcasses of larger marine animals. This marine snow acts as a steady conveyor belt, transporting our chemical legacy down into the abyss, where scavengers like Hirandelia gigas eagerly consume it, unwittingly absorbing the toxins into their own bodies. This mechanism of contamination was further illuminated just a year later, when Jameson returned with another alarming revelation about the state of the deep sea. In 2018, his team published findings detailing the presence of microplastics in the deepest parts of the ocean, recovering synthetic fibers and plastic fragments at a staggering depth of 10,190 meters. They examined amphipods from 6 different deep ocean trenches across the Pacific Rim, from Japan to South America. In every single trench, they found animals that had ingested plastic, proving that microplastic pollution is not a localized issue, but a pervasive reality of the Hadal environment. The implications for Hadal ecology are profound and deeply troubling. These microscopic fragments of plastic, along with the chemical pollutants they carry, are now an integral part of the deep-sea food web. Because the abyssal environment is so cold and subject to such immense pressure, the chemical degradation of these materials is incredibly slow, meaning they will persist in this hidden realm for centuries. We are forced to confront the reality that we have fundamentally altered the chemistry of the deep ocean before we have even begun to fully understand its biology. The vertical transport of particles is just one way the ocean connects the surface to the deep, but there is a much grander system at work, one that operates on a planetary scale. This is the thermohaline circulation, often referred to as the global ocean conveyor belt. It is a massive, slowly moving system of deep ocean currents driven by subtle differences in the water's temperature and salinity. The word thermohaline is derived from thermo, meaning temperature, and haline, meaning salt, and these two factors combined dictate the density of seawater, driving the most powerful underwater rivers on Earth. In the frigid regions of the North Atlantic and around the icy continent of Antarctica, surface water is subjected to intense cold and fierce winter winds. As the ocean water freezes to form sea ice, it leaves its salt behind in the surrounding water, a process known as brine rejection. This newly chilled, highly saline water becomes incredibly dense and heavy, causing it to sink rapidly toward the ocean floor. This sinking creates immense masses of dense liquid, known as North Atlantic deep water and Antarctic bottom water, which begin a slow, creeping journey across the abyssal plains. These deep water masses travel relentlessly through the ocean basins, sliding beneath warmer, lighter waters and carving invisible paths across the ocean floor. The journey of the global ocean conveyor belt is agonizingly slow, a far cry from the swift surface currents driven by the wind. It takes centuries, sometimes up to a millennium, for a single parcel of deep water to complete its circuit around the globe, eventually slowly rising back to the surface in distant regions like the Indian and Pacific Oceans. This vast circulation system is the true beating heart of the planet, distributing heat, regulating the global climate, and transporting dissolved oxygen into the deep sea to sustain life in the darkness. However, this immense planetary engine is not as stable as we once believed, and recent observations suggest that the Atlantic Meridional Overturning Circulation, or AMOC, is showing signs of weakening. The AMOC is a crucial component of the global conveyor belt, responsible for pulling warm, salty water from the tropics up toward the North Atlantic, where it cools, sinks, and flows southward again. As global temperatures rise and the Greenland ice sheet melts at an accelerating rate, massive volumes of fresh water are pouring into the North Atlantic. This influx of fresh, less dense water acts as a braking mechanism, disrupting the delicate balance of density that drives the sinking process. The evidence of this slowing circulation is hidden in oceanographic data and paleoclimate records, which provide analogs for what might happen if the AMOC were to collapse entirely. By studying deep-sea sediment cores and ancient ice layers, scientists have found periods in Earth's history where immense influxes of glacial meltwater rapidly shut down this oceanic conveyor belt. The consequences were drastic and immediate, leading to sudden, severe drops in temperature across the northern hemisphere. If the AMOC continues to weaken today, we would face profound disruptions to the climate we have come to rely on. A significantly weakened AMOC would mean that less heat is transported from the equator to the northern latitudes, leading to paradoxically colder winter temperatures across Western Europe, even as the rest of the globe warms. Furthermore, this disruption would have catastrophic effects on global fisheries, as the circulation system is responsible for dredging up vital nutrients from the deep sea to fertilize the surface waters. Without this constant churning and nutrient recycling, the highly productive marine ecosystems that support millions of people would face collapse, demonstrating just how heavily our survival depends on the silent, slow-moving currents of the abyss. As we look deeper into the history of the ocean, we find that its ancient past is just as mysterious and confounding as its physical processes. The life that once inhabited these prehistoric waters challenges our modern attempts at classification, reminding us that evolution has experimented with forms so bizarre they defy logic. In the fossil beds of the Mazon Creek Formation in Illinois, scientists discovered the remains of a creature that lived roughly 300 million years ago, a marine animal so utterly strange it became known simply as the Tully monster. Tullimonstrum gregarium was a soft-bodied creature that resembled nothing alive today, featuring a torpedo-shaped body, eyes set on the ends of a rigid bar spanning its head, and a long, flexible snout tipped with a claw-like appendage full of sharp teeth. For over half a century, the taxonomy of this bizarre animal was fiercely debated, as paleontologists struggled to determine where it belonged on the tree of life. It lacked the hard parts that normally fossilize well, leaving behind only flattened, ghostly impressions in the ancient rock, which offered conflicting clues about its anatomy. It was not until 2016 that a team led by researcher Victoria McCoy used advanced imaging techniques to analyze over 1,000 Tully monster fossils, finally bringing some clarity to this enduring mystery. McCoy and her colleagues identified a light-colored band running down the creature's back as a notochord, a primitive backbone, along with gill pouches and a sophisticated nervous system. This allowed them to classify the Tully monster as a vertebrate, specifically a jawless chordate related to modern lampreys. Yet, even with this classification, the creature remains a profound lesson in the sheer strangeness of ancient ocean life, reminding us that our neat taxonomic boxes are entirely inadequate when faced with the boundless creativity of evolution. This astonishing evolutionary creativity is not confined to the deep past, as the modern ocean continues to hide creatures that stretch the limits of our imagination. In the dark twilight zone of the deep sea, where the last traces of sunlight fade into absolute blackness, lives a fish that seems to have been engineered by science fiction. This is the barrel-eye fish, Macropinna microstoma, a creature possessing a transparent fluid-filled dome on its head that reveals the internal structure of its skull. Inside this transparent shield sit two large, vivid green tubular eyes, pointing straight upward through the top of its head to scan the darkness above for the faint silhouettes of prey. For decades, the true nature of the barrel-eye fish remained a mystery, as specimens brought up in trawling nets were always severely damaged by the immense change in pressure, their delicate, transparent domes destroyed. It was assumed that their strange, upward-looking eyes were fixed in place, providing a very limited field of vision. However, in 2009, researchers Bruce Robison and Kim Reisenbichler at the Monterey Bay Aquarium Research Institute, or MBARI, finally observed a living barrel-eye fish in its natural habitat using a remotely operated vehicle. What they witnessed profoundly changed our understanding of this bizarre animal. They discovered that the barrel-eye's tubular eyes are not fixed at all, but can actually rotate within the fluid-filled shield of its transparent head. When the fish spots a drifting jellyfish or small crustacean above, it pivots its body vertically to feed, simultaneously rotating its eyes forward to lock onto its target. This incredible adaptation allows the fish to protect its sensitive eyes from the stinging tentacles of siphonophores while maintaining a constant visual lock on its prey. The fact that such a complex and bizarre mechanism remained completely unknown until 2009 is a humbling reminder of how much we have missed, even in the relatively accessible depth ranges of the ocean. The depths are filled with such specialized optical adaptations, as survival in the twilight zone depends entirely on capturing the faintest glimmers of light. Another extraordinary example is Bathylichnops exilis, a deep-sea fish that has seemingly evolved 4 eyes to navigate the gloom. In addition to a pair of large, upward-looking primary eyes, this species possesses a secondary set of smaller eye-like organs situated on the sides of its head, pointing downward. These secondary structures contain a lens and retina of their own, allowing the fish to simultaneously monitor the water below it for bioluminescent flashes, effectively giving it a wide, multi-directional view of its dark environment. These incredible creatures demonstrate how the physical constraints of the ocean, the crushing pressure, the pervasive cold, and the absolute darkness force life to adapt in ways that seem entirely alien to us. Yet, it is not just the deep, dark abyss that holds mysteries and paradoxes, for even the most productive and sunlit regions of the ocean are governed by profound contradictions. Off the western coast of South America, the Humboldt Current drives an oceanic engine that creates the richest fishing grounds on Earth. Here, relentless winds push warm surface waters offshore, allowing incredibly cold, nutrient-dense water from the deep sea to well up to the surface. This upwelling phenomenon floods the sunlit waters with nitrates and phosphates, sparking massive, explosive blooms of phytoplankton that form the base of an enormous food web. These phytoplankton support immense shoals of anchovies and sardines, which in turn feed seabirds, marine mammals, and a massive human fishing industry. The sheer abundance of life in the Humboldt Current is breathtaking, an explosion of biomass that seems to defy the harsh, arid landscapes of the nearby Peruvian coast. But this incredible surface productivity hides a dark and suffocating reality just a few hundred meters below the waves. Directly beneath this thriving ecosystem lies a massive oxygen minimum zone, a vast expanse of water where dissolved oxygen levels plummet to near zero. As the billions of phytoplankton at the surface die, they sink into the deeper waters, where vast armies of bacteria consume them. The bacteria use up almost all the available oxygen in the water to decompose this endless rain of organic matter, creating a suffocating dead zone where very few animals can survive. It is a profound paradox that the exact same physical forces that create the most vibrant, life-sustaining ecosystem at the surface simultaneously generate a vast, anoxic wasteland right beneath it, a contradiction that the ocean carries without apology, as the same currents that feed millions. It is a profound paradox that the exact same physical forces that create the most vibrant, life-sustaining ecosystem at the surface simultaneously generate a vast, anoxic wasteland right beneath it. A contradiction that the ocean carries without apology, as the same currents that feed millions of organisms above also strip the oxygen from the depths below. This delicate balance of life and absence, of abundance and depletion, is a recurring theme in the intricate tapestry of the global ocean. We find ourselves constantly returning to the surface, drawn to the intersection of water and light, where the fundamental chemistry of our planet is continuously rewritten on a microscopic scale. Here, in the sunlit upper layers, an invisible but monumental process unfolds every second of every day. The ocean is not merely a basin of water, it is a vast planetary lung, breathing life into the atmosphere. When we take a breath, filling our own lungs with the crisp, life-giving air, we rarely pause to consider the origin of that oxygen. Yet, 50% of all the atmospheric oxygen on Earth is produced not by the sprawling rainforests or the dense terrestrial woodlands, but by marine phytoplankton drifting silently in the ocean currents. These microscopic architects of our atmosphere are incredibly diverse, comprising a myriad of single-celled organisms that harness the power of the sun. Among them, the diatoms construct intricate glass-like shells of silica, their forms resembling perfectly symmetrical jewels suspended in the water column. The cyanobacteria, ancient and resilient, have been photosynthesizing for billions of years, slowly shaping the early Earth into a habitable world. The dinoflagellates, with their whip-like tails, navigate the microcurrents, some even producing the ethereal glow of bioluminescence when disturbed. Together, this invisible forest operates on a scale so vast that it dictates the composition of the very air we breathe. They are the silent engine of the global carbon cycle, drawing down carbon dioxide from the atmosphere and releasing oxygen in a relentless, continuous exchange. Within this microscopic realm, there exists one organism of particular note, a creature so small and unassuming that its existence remained entirely unknown to science until the late 20th century. In 1986, the biological oceanographer Penny Chisholm and her colleagues discovered the Prochlorococcus genus. This tiny cyanobacterium is the smallest known photosynthetic organism on our planet, yet it is also the most abundant. It is estimated that there are octillions of Prochlorococcus cells in the global ocean, a number so large it defies human comprehension. They drift in the vast oceanic gyres, quietly turning sunlight and inorganic compounds into the organic matter that fuels the entire marine food web. The discovery of Prochlorococcus fundamentally shifted our understanding of the ocean's role as an oxygen factory. It revealed that the foundations of life are often laid by the smallest, most overlooked participants in the ecosystem. Every other breath you take is a gift from these invisible multitudes, a quiet offering from the surface of the sea to the terrestrial world. As we drift away from the sunlit surface and begin our long descent into the darker depths, the vibrant activity of the phytoplankton fades, replaced by a profound and expansive silence. The ocean floor is not a flat, featureless plain, but a dynamic, geological landscape of immense proportions. As we scan the deep ocean basin, our instruments reveal the presence of abyssal hills, the most common landform on the planet Earth. These low, rolling ridges stretch out across the seafloor in parallel lines, covering over 80% of the ocean bottom. Despite their ubiquity, they remain one of the least studied geological features of our world. We know more about the craters on the dark side of the moon than we do about the abyssal hills that dominate our own planet. They are born in the fiery depths of the Earth, formed by the relentless process of tectonic spreading. As the great crustal plates pull apart along the mid-ocean ridges, molten rock rises to fill the void, cooling and solidifying upon contact with the frigid bottom waters. The periodic earthquakes that shudder along these fault lines fracture the newly formed crust, creating a series of ridges and valleys that are slowly pushed outward, migrating across the abyssal plain over millions of years. They are monuments to the slow, steady heartbeat of the Earth's interior, covered over time by a gentle, continuous accumulation of deep-sea sediment. Their vast, undulating expanses remain largely unmapped, cloaked in the eternal darkness of the deep, guarding their secrets in silent endurance. Among these rolling hills and vast plains, life still endures, adapted to a world characterized by crushing pressure, near-freezing temperatures, and absolute darkness. In the late 19th century, during a pioneering deep-sea dredging expedition in 1879, scientists pulled up a creature that seemed to defy the natural order of things. It was the giant isopod, scientifically known as Bathynomus giganteus. Reaching up to 50 centimeters in length, it is a magnificent armored scavenger of the deep. If you were to look closely at its segmented body and complex, multifaceted eyes, you would notice a striking resemblance to the common pillbug found in gardens and under damp logs. They are, in fact, closely related, sharing the same basic crustacean lineage, though separated by millions of years of divergent evolution. The giant isopod is a master of survival in an environment where resources are remarkably scarce. In the deep sea, food does not grow, it must fall from the productive layers far above. Meals are unpredictable, sometimes arriving as the massive carcass of a whale, and other times not arriving at all for extended periods. To cope with this feast or famine existence, Bathynomus giganteus has developed an incredibly slow metabolism. It can go for months, and in some documented cases, even years, without a single morsel of food. When starvation sets in, the isopod enters a state of deep physiological suspension, a kind of zombie mode, where its metabolic rate drops to the absolute minimum required to sustain life. It waits, motionless in the dark, preserving its energy, an enduring testament to the resilience of life in the most unforgiving corners of the Earth. Its existence reveals the extreme physiological adaptations that the deep sea demands of its inhabitants. Continuing our descent, we pass beyond the reach of any surface light, entering the realm known as the bathypelagic zone, or the midnight zone. Stretching from 1,000 to 4,000 meters below the surface, this is a world defined by the complete absence of sunlight. Here, no photosynthesis is possible. The only light that exists is the cold, intermittent flash of bioluminescence, produced by the organisms themselves. The physical conditions are extreme. The pressure is immense, capable of crushing anything not perfectly adapted to it, and the temperature hovers just a few degrees above freezing. Yet, this is not a barren void, but an active three-dimensional hunting ground. It is the domain of the giant squid, ghosting through the water with huge, sensitive eyes, searching for prey in the absolute dark. It is also the home of the anglerfish, a creature that has turned the darkness to its advantage by evolving a glowing lure on a modified dorsal fin to attract curious prey directly toward its formidable jaws. And perhaps most fascinating of all is the dragonfish, a family of deep-sea predators known scientifically as Stomiidae. The dragonfish is a marvel of evolutionary engineering. Its body is elongated and dark, rendering it nearly invisible in the bathypelagic gloom. But it is the jaw of the dragonfish that truly distinguishes it. It is equipped with oversized, needle-like teeth that are completely transparent. In a world where any reflection of bioluminescent light could give away a predator's position, these clear teeth ensure that the dragonfish remains an unseen threat until it is far too late for its prey to escape. But the dragonfish holds another, even more remarkable secret. While the vast majority of deep-sea animals produce and see only blue or green bioluminescence, because those wavelengths travel furthest through the water, the dragonfish of the genus Aristostomias scintillans can produce and see red bioluminescence. In the deep ocean, red light is the first color to be absorbed by water, so most deep-sea creatures have lost the ability to see it altogether. To them, red is synonymous with black. The dragonfish uses this biological blind spot to its extraordinary advantage. It emits a beam of red light from organs beneath its eyes, sweeping the dark water like a sniper's invisible searchlight. It can illuminate its prey without the prey ever knowing it has been spotted, a silent, deadly advantage in the perpetual midnight of the deep sea. Beneath the midnight zone, settling over the abyssal hills and plains, lies a thick, soft blanket of deep-sea sediment. This sediment is more than just mud. It is an ancient, undisturbed archive of Earth's planetary history. For millions of years, particles have been raining down from the surface, accumulating layer by painstaking layer on the ocean floor. Every shift in the climate, every change in the ocean's chemistry, every mass extinction and evolutionary bloom is recorded in the composition of these sediments. To read this archive, we rely on scientific drilling ships like the JOIDES Resolution. This remarkable vessel serves as a floating laboratory, capable of lowering miles of drill pipe down through the water column and into the seafloor, extracting long, cylindrical cores of sediment that bring the past back to the surface. In these cores, scientists can trace the shifting patterns of global temperatures and ocean currents. A particularly significant core was extracted from a region known as the Walvis Ridge, an underwater mountain range in the South Atlantic. This core revealed a distinct, dark layer of clay, devoid of the usual calcium carbonate shells of microorganisms, dating back exactly 55 million years. This layer corresponds to an event known as the Paleocene-Eocene thermal maximum, a period of rapid, intense global warming driven by a massive release of carbon dioxide into the atmosphere. The sediment record showed that the ocean absorbed so much carbon that it became highly acidic, dissolving the shells of marine life and leaving behind only that dark layer of clay. By studying this ancient acidification event, we gain critical insights into the modern ocean, understanding how the current influx of atmospheric carbon might alter the delicate chemical balance of the sea today. The sediment archive is built upon a continuous, gentle snowfall, a phenomenon appropriately named marine snow. It is the slow drift of organic material from the productive surface waters down to the deep ocean. This marine snow is composed of a complex mixture of materials, a detrital rain of the ocean's biological byproducts. It includes the microscopic shells of dead phytoplankton, the remains of zooplankton, tiny flecks of soot, and the gelatinous abandoned houses of larvaceans. Importantly, It is heavily composed of fecal pellets produced by small grazing organisms, which act as dense little packages of carbon, sinking rapidly through the water column. As these various tiny particles drift downward, they bump into one another, sticking together to form larger, more complex masses known as marine aggregates. The speed at which this marine snow sinks is highly variable, ranging anywhere from 1 to 100 meters per day. The pace of the descent is a critical factor in the deep ocean's carbon cycle. Faster sinking particles, those heavy, dense aggregates, are more likely to reach the abyssal depths relatively intact, successfully delivering their payload of nutrients and carbon to the hungry ecosystem below. Slower particles may be intercepted and consumed by the inhabitants of the midwater, their energy recycled before they ever reach the bottom. It is this continuous silent drift of marine snow that binds the disparate layers of the ocean together, a lifeline of sustenance flowing from the bright, chaotic surface down to the patient, enduring dark. Every single particle of marine snow carries a history, a microscopic record of the life it once was, slowly descending through the vast, quiet water column. The journey of a single aggregate can take weeks or even months, depending on its density and the intricate shifting currents of the deep ocean. As it falls, it passes through layers of water that change imperceptibly in temperature and pressure. The surface waters, warmed by the sun and agitated by the wind, slowly give way to the thermocline, a region of rapid temperature decrease. Below this, the water becomes frigid and still, creating an environment where the slow drift of the snow is the only measure of time. Consider the diatoms, those microscopic, glass-shelled architects of the surface ocean. When a diatom dies, its delicate silica shell begins its long descent. For a time, it may remain suspended in the upper layers, drifting on the unseen currents. But eventually it will bump into other sinking particles, perhaps the discarded molt of a tiny copepod or the carbon-rich fecal pellet of a passing salp. These particles adhere to one another, bound by sticky, transparent sugars exuded by marine bacteria. This newly formed aggregate, now heavier and more dense, begins to sink with greater purpose. It becomes a microhabitat in its own right, colonized by specialized bacteria that break down its organic matter as it falls. As this aggregate descends into the mesopelagic zone, the twilight zone of the ocean, it enters a dangerous realm. Here, a myriad of creatures wait, suspended in the dim blue light, ready to intercept the falling snow. Delicate, transparent jellyfish trail their tentacles, hoping to snare passing aggregates. Vampire squids, with their velvet black cloaks, deploy long, sticky filaments to capture the snow, drawing it back to their mouths in a slow, continuous feeding process. The aggregate may be partially consumed, broken apart, and then repackaged as a new fecal pellet, restarting its journey to the depths below. This constant recycling, this continuous breaking down and building up, is the fundamental rhythm of the midwater ecosystem. For the particles that survive this gauntlet, the journey continues into the bathypelagic zone, the midnight realm. In this absolute darkness, the marine snow is the only reliable source of sustenance for the creatures that dwell in the permanent night. The anglerfish waits patiently, conserving its energy, while the giant squid prowls the darkness, its massive eyes tuned to detect the faint, bioluminescent flashes of creatures disturbed by the falling snow. The dragonfish sweeps its red bioluminescent searchlight, seeking out prey that has gathered to feed on the sinking aggregates. The snow is the bait, the lure that draws the entire deep-sea food web together in a delicate, deadly dance. And yet, despite the relentless predation of the midwater, a significant portion of the marine snow continues its descent, falling deeper and deeper into the abyss. Here, the water is near freezing, the pressure is crushing, and the darkness is absolute. This is the domain of the abyssal hills, those vast, rolling ridges that stretch across the seafloor. As the marine snow finally settles upon this ancient landscape, it joins the great sediment archive, adding another microscopic layer to the millions of years of accumulated history. This is where the giant isopod, Bathynomus giganteus, prowls the soft, muddy bottom, moving with deliberate, armored grace across the sediment. It leaves faint, temporary tracks in the mud, delicate etchings that are soon erased by the continuing drift of the marine snow. It is a solitary wanderer in an unimaginably vast desert, a creature defined by its ability to endure. The long periods of starvation, the deep physiological suspension, are not merely survival strategies, they are the defining characteristics of existence in the abyss. Here, life moves at a glacial pace, energy is conserved at all costs, and patience is the ultimate virtue, as the ocean settles into a quiet so complete and a darkness so absolute that time itself seems to slow, each particle of marine snow marking its own unhurried passage from the bright world above into the ancient, unchanging depths below, carrying the story of the surface into a silence that has persisted for longer than we can fully comprehend. This interconnected nature of the global ocean means that no single ecosystem exists in true isolation from the rest. The silence of the deep ocean is punctuated only by the slow, inevitable drift of marine snow. We find that the forces governing the surface waters are inextricably linked to the dark abyss. The ocean operates as a single, vast entity, circulating energy and matter across thousands of miles. This continuous exchange of water masses shapes the conditions of life far below the reach of sunlight. This is a realm where the frantic pace of the surface is forgotten, replaced by a slow, enduring rhythm. The ancient rocks of the seafloor stand as silent witnesses to the slow, tectonic shifting of the Earth's crust. The deep ocean currents act as a global conveyor belt, distributing heat and nutrients in a slow, planetary waltz. Here, the darkness is absolute, a pervasive shadow that stretches endlessly in every direction. The temperature here hovers just above freezing, slowing down the metabolic rates of the creatures that navigate the dark. There is a profound stillness in these waters, a quiet that has remained unbroken for millions of years. This unseen world, though remote and alien, is fundamentally tied to the health and balance of the entire planet. The steady accumulation of sediment slowly buries the past, layer upon microscopic layer, in the quiet depths. This unseen world, though remote and alien, is fundamentally tied to the health and balance of the entire planet. Life here moves at a glacial pace, a testament to the enduring patience required to inhabit the deep ocean. The temperature here hovers just above freezing, slowing down the metabolic rates of the creatures that navigate the dark. The deep ocean currents act as a global conveyor belt, distributing heat and nutrients in a slow planetary waltz. Rising from the abyssal plains are the solitary giants of the deep known as seamounts. These immense underwater mountains are formed by ancient volcanic activity, pushing upward through the oceanic crust. Current estimates suggest there are over 30,000 seamounts distributed across the global ocean. Despite their staggering numbers, fewer than 300 have been comprehensively surveyed by biologists. These structures create massive obstacles for deep ocean currents, forcing nutrient-rich water upward. The steady accumulation of sediment slowly buries the past, layer upon microscopic layer, in the quiet depths. This is a realm where the frantic pace of the surface is forgotten, replaced by a slow, enduring rhythm. Every movement in the abyss is deliberate, a conservation of precious energy in a world where food is scarce. The immense pressure at these depths acts as a constant, invisible force, shaping the very biology of everything that dwells here. The steady accumulation of sediment slowly buries the past, layer upon microscopic layer, in the quiet depths. The temperature here hovers just above freezing, slowing down the metabolic rates of the creatures that navigate the dark. The chemical composition of these waters holds a subtle record of the ocean's vast, interconnected circulatory system. The ocean floor undulates in slow, muddy dunes, shaped by the gentle caress of deep-sea currents. The sheer volume of water overhead is incomprehensible, a liquid sky that presses down with unrelenting weight. The ancient rocks of the seafloor stand as silent witnesses to the slow, tectonic shifting of the Earth's crust. The immense pressure at these depths acts as a constant, invisible force, shaping the very biology of everything that dwells here. The temperature here hovers just above freezing, slowing down the metabolic rates of the creatures that navigate the dark. The deflection of deep currents by seamounts creates localized upwellings of remarkable productivity. This localized enrichment transforms seamounts into vital oases of biodiversity amidst the relatively barren abyssal plains. Corals and sponges attached to the rocky substrates, providing habitat for a myriad of other species. The isolation of these seamounts often functions similarly to islands on land. Many species found on a given seamount are endemic, existing nowhere else in the world. The deep ocean currents act as a global conveyor belt, distributing heat and nutrients in a slow planetary waltz. This unseen world, though remote and alien, is fundamentally tied to the health and balance of the entire planet. The geological clock ticks softly in the deep, measuring time not in days or years, but in millennia and epochs. The steady accumulation of sediment slowly buries the past, layer upon microscopic layer, in the quiet depths. The ocean floor undulates in slow, muddy dunes, shaped by the gentle caress of deep-sea currents. The geological clock ticks softly in the deep, measuring time not in days or years, but in millennia and epochs. This unseen world, though remote and alien, is fundamentally tied to the health and balance of the entire planet. The immense pressure at these depths acts as a constant, invisible force, shaping the very biology of everything that dwells here. The chemical composition of these waters holds a subtle record of the ocean's vast, interconnected circulatory system. The steady accumulation of sediment slowly buries the past, layer upon microscopic layer, in the quiet depths. Life here moves at a glacial pace, a testament to the enduring patience required to inhabit the deep ocean. The deep ocean currents act as a global conveyor belt, distributing heat and nutrients in a slow planetary waltz. The biological isolation of seamounts allows for unique evolutionary pathways to unfold over millions of years. Fish species congregate around these peaks, taking advantage of the concentrated food resources. The fragile coral frameworks that build up on seamounts grow at imperceptibly slow rates. Some deep-water coral colonies are thousands of years old, recording the history of the ocean in their skeletons. Their slow growth makes them exceptionally vulnerable to physical disturbances, particularly from deep-sea trawling operations. The ocean floor undulates in slow, muddy dunes, shaped by the gentle caress of deep-sea currents. The chemical composition of these waters holds a subtle record of the ocean's vast, interconnected circulatory system. There is a profound stillness in these waters, a quiet that has remained unbroken for millions of years. The silence is vast and enveloping, offering a stark contrast to the noisy, sunlit world far above. This unseen world, though remote and alien, is fundamentally tied to the health and balance of the entire planet. The silence is vast and enveloping, offering a stark contrast to the noisy, sunlit world far above. This is a realm where the frantic pace of the surface is forgotten, replaced by a slow, enduring rhythm. There is a profound stillness in these waters, a quiet that has remained unbroken for millions of years. Each descending particle of organic matter carries a fraction of the surface's vitality down into the waiting abyss. Here, the darkness is absolute, a pervasive shadow that stretches endlessly in every direction. This is a realm where the frantic pace of the surface is forgotten, replaced by a slow, enduring rhythm. Every movement in the abyss is deliberate, a conservation of precious energy in a world where food is scarce. Moving away from the isolated peaks of seamounts, we encounter the vast, circular current systems of the open ocean. The North Pacific Gyre is one of the most prominent of these planetary-scale circulation patterns. Driven by the rotation of the Earth and global wind patterns, this massive gyre rotates slowly and endlessly. The gyre serves as a profound demonstration of the ocean's physical dynamics and its capacity to transport materials. It gathers the waters of the North Pacific into a slowly rotating vortex thousands of miles across. The steady accumulation of sediment slowly buries the past, layer upon microscopic layer in the quiet depths. The chemical composition of these waters holds a subtle record of the ocean's vast, interconnected circulatory system. The sheer volume of water overhead is incomprehensible, a liquid sky that presses down with unrelenting weight. The deep ocean currents act as a global conveyor belt, distributing heat and nutrients in a slow, planetary waltz. The immense pressure at these depths acts as a constant, invisible force, shaping the very biology of everything that dwells here. The ocean floor undulates in slow, muddy dunes, shaped by the gentle caress of deep-sea currents. The chemical composition of these waters holds a subtle record of the ocean's vast, interconnected circulatory system. The temperature here hovers just above freezing, slowing down the metabolic rates of the creatures that navigate the dark. The geological clock ticks softly in the deep, measuring time not in days or years, but in millennia and epochs. The ocean floor undulates in slow, muddy dunes, shaped by the gentle caress of deep-sea currents. Each descending particle of organic matter carries a fraction of the surface's vitality down into the waiting abyss. The temperature here hovers just above freezing, slowing down the metabolic rates of the creatures that navigate the dark. In recent decades, this natural circulation pattern has begun to reveal the extensive reach of human influence. The convergence of currents within the North Pacific Gyre traps floating materials, accumulating vast quantities of marine debris. Much of this material is plastic, slowly breaking down into smaller fragments under the influence of sunlight and wave action. This accumulation zone highlights the inescapable connectivity of the global ocean. Materials introduced into coastal waters can eventually find their way to the most remote regions of the sea. The sheer volume of water overhead is incomprehensible, a liquid sky that presses down with unrelenting weight. Every movement in the abyss is deliberate, a conservation of precious energy in a world where food is scarce. The ancient rocks of the seafloor stand as silent witnesses to the slow tectonic shifting of the Earth's crust. Here, the darkness is absolute, a pervasive shadow that stretches endlessly in every direction. The ocean floor undulates in slow, muddy dunes, shaped by the gentle caress of deep sea currents. This unseen world, though remote and alien, is fundamentally tied to the health and balance of the entire planet. The sheer volume of water overhead is incomprehensible, a liquid sky that presses down with unrelenting weight. The silence is vast and enveloping, offering a stark contrast to the noisy, sunlit world far above. The ocean floor undulates in slow, muddy dunes, shaped by the gentle caress of deep-sea currents. The slow drift of water masses brings subtle shifts in chemistry, dictating the distribution of microscopic life. This is a realm where the frantic pace of the surface is forgotten, replaced by a slow, enduring rhythm. There is a profound stillness in these waters, a quiet that has remained unbroken for millions of years. The physics of the ocean dictate that these circular currents will persist, continuing to gather whatever floats upon the surface. The deep waters beneath the gyre remain largely isolated from the immediate effects of this surface accumulation. However, the slow sinking of microplastics and other materials demonstrates that even the abyss is not entirely disconnected. We are only beginning to understand the long-term implications of this widespread distribution of artificial materials. The ocean's currents, ancient and powerful, now carry a novel signature of the modern era. The immense pressure at these depths acts as a constant, invisible force, shaping the very biology of everything that dwells here. This is a realm where the frantic pace of the surface is forgotten, replaced by a slow, enduring rhythm. In this extreme environment, survival requires remarkable adaptations, biochemical miracles forged in the crushing deep. The deep ocean currents act as a global conveyor belt, distributing heat and nutrients in a slow, planetary waltz. In this extreme environment, survival requires remarkable adaptations, biochemical miracles forged in the crushing deep. Here, the darkness is absolute, a pervasive shadow that stretches endlessly in every direction. This unseen world, though remote and alien, is fundamentally tied to the health and balance of the entire planet. The immense pressure at these depths acts as a constant, invisible force, shaping the very biology of everything that dwells here. Here, the darkness is absolute, a pervasive shadow that stretches endlessly in every direction. There is a profound stillness in these waters, a quiet that has remained unbroken for millions of years. The chemical composition of these waters holds a subtle record of the ocean's vast, interconnected circulatory system. This is a realm where the frantic pace of the surface is forgotten, replaced by a slow, enduring rhythm. Far from the open waters of the Pacific, the Gulf of Mexico and the Red Sea conceal a different kind of marvel. Here, in the profound depths, we find actual lakes resting on the ocean floor. These are the brine pools, extraordinary geological formations characterized by extreme salinity. The water within these pools is several times saltier than the surrounding ocean, making it significantly denser. This high density prevents the brine from mixing with the seawater above, creating a distinct interface. The temperature here hovers just above freezing, slowing down the metabolic rates of the creatures that navigate the dark. The chemical composition of these waters holds a subtle record of the ocean's vast, interconnected circulatory system. In this extreme environment, survival requires remarkable adaptations, biochemical miracles forged in the crushing deep. The immense pressure at these depths acts as a constant, invisible force, shaping the very biology of everything that dwells here. Within this boundless dark, Occasional flashes of bioluminescence serve as fleeting, brilliant reminders of life. The ancient rocks of the seafloor stand as silent witnesses to the slow, tectonic shifting of the Earth's crust. The silence is vast and enveloping, offering a stark contrast to the noisy, sunlit world far above. This is a realm where the frantic pace of the surface is forgotten, replaced by a slow, enduring rhythm. The sheer volume of water overhead is incomprehensible, a liquid sky that presses down with unrelenting weight. The ocean floor undulates in slow, muddy dunes, shaped by the gentle caress of deep-sea currents. Every movement in the abyss is deliberate, a conservation of precious energy in a world where food is scarce. The deep ocean currents act as a global conveyor belt, distributing heat and nutrients in a slow, planetary waltz. The surface of a brine pool resembles a mirror, reflecting the lights of deep-sea submersibles. This boundary is sharp and visually striking, complete with ripples that mimic the surface of a terrestrial lake. However, this fascinating environment is highly toxic to most marine life. The concentrated brine is devoid of oxygen and often rich in toxic compounds like hydrogen sulfide and methane. Animals that accidentally swim into the pool often suffer immediate shock and perish. Life here moves at a glacial pace, a testament to the enduring patience required to inhabit the deep ocean. This is a realm where the frantic pace of the surface is forgotten, replaced by a slow, enduring rhythm. The ancient rocks of the seafloor stand as silent witnesses to the slow, tectonic shifting of the Earth's crust. There is a profound stillness in these waters, a quiet that has remained unbroken for millions of years. This unseen world, though remote and alien, is fundamentally tied to the health and balance of the entire planet. Here, the darkness is absolute, a pervasive shadow that stretches endlessly in every direction. The geological clock ticks softly in the deep, measuring time not in days or years, but in millennia and epochs. The slow drift of water masses brings subtle shifts in chemistry, dictating the distribution of microscopic life. There is a profound stillness in these waters, a quiet that has remained unbroken for millions of years. The immense pressure at these depths acts as a constant, invisible force, shaping the very biology of everything that dwells here. Every movement in the abyss is deliberate, a conservation of precious energy in a world where food is scarce. The deep ocean currents act as a global conveyor belt, distributing heat and nutrients in a slow planetary waltz. Despite the lethality of the brine itself, the shores of these underwater lakes are teeming with specialized life. Extreme halophile communities, organisms adapted to incredibly high salt concentrations, thrive along the edges. Chemosynthetic bacteria form thick mats, utilizing the methane and sulfides seeping from the pool. Mussels and tube worms form dense beds around the perimeter, relying on symbiotic relationships with these bacteria. These thriving communities demonstrate the astonishing adaptability of life in the most hostile environments imaginable. The sheer volume of water overhead is incomprehensible, a liquid sky that presses down with unrelenting weight. There is a profound stillness in these waters, a quiet that has remained unbroken for millions of years. The temperature here hovers just above freezing, slowing down the metabolic rates of the creatures that navigate the dark. This unseen world, though remote and alien, is fundamentally tied to the health and balance of the entire planet. Here, the darkness is absolute, a pervasive shadow that stretches endlessly in every direction. The deep ocean currents act as a global conveyor belt, distributing heat and nutrients in a slow, planetary waltz. The slow drift of water masses brings subtle shifts in chemistry, dictating the distribution of microscopic life. The chemical composition of these waters holds a subtle record of the ocean's vast, interconnected circulatory system. Each descending particle of organic matter carries a fraction of the surface's vitality down into the waiting abyss. The immense pressure at these depths acts as a constant, invisible force, shaping the very biology of everything that dwells here. The geological clock ticks softly in the deep, measuring time not in days or years, but in millennia and epochs. The steady accumulation of sediment slowly buries the past, layer upon microscopic layer in the quiet depths. In the vast expanse of the North Atlantic, another unique marine environment is defined not by land, but by water. The Sargasso Sea is the only sea on Earth without a land boundary. It is bounded entirely by the circulating currents of the North Atlantic Gyre. The sea takes its name from the sargassum seaweed that floats in massive golden-brown mats upon its surface. This floating ecosystem provides crucial shelter and foraging grounds for countless marine species. The immense pressure at these depths acts as a constant, invisible force, shaping the very biology of everything that dwells here. The geological clock ticks softly in the deep, measuring time not in days or years but in millennia and epochs. There is a profound stillness in these waters, a quiet that has remained unbroken for millions of years. Every movement in the abyss is deliberate, a conservation of precious energy in a world where food is scarce. In this extreme environment, survival requires remarkable adaptations, biochemical miracles forged in the crushing deep. The chemical composition of these waters holds a subtle record of the ocean's vast, interconnected circulatory system. The immense pressure at these depths acts as a constant, invisible force, shaping the very biology of everything that dwells here. This unseen world, though remote and alien, is fundamentally tied to the health and balance of the entire planet. The sheer volume of water overhead is incomprehensible, a liquid sky that presses down with unrelenting weight. Life here moves at a glacial pace, a testament to the enduring patience required to inhabit the deep ocean. The chemical composition of these waters holds a subtle record of the ocean's vast, interconnected circulatory system. The temperature here hovers just above freezing, slowing down the metabolic rates of the creatures that navigate the dark. The Sargasso Sea holds one of the most enduring mysteries of marine biology. It is the destination for both European and American eels, species known scientifically as Anguilla anguilla and Anguilla rostrata. These eels spend their adult lives in freshwater rivers and estuaries across 2 continents. When the time comes to reproduce, they undertake epic thousands-of-mile migrations back to the Sargasso Sea. The exact mechanism they use to navigate across the featureless ocean remains a subject of intense scientific study. The chemical composition of these waters holds a subtle record of the ocean's vast, interconnected circulatory system. The immense pressure at these depths acts as a constant, invisible force, shaping the very biology of everything that dwells here. The deep ocean currents act as a global conveyor belt, distributing heat and nutrients in a slow, planetary waltz. The temperature here hovers just above freezing, slowing down the metabolic rates of the creatures that navigate the dark. The silence is vast and enveloping, offering a stark contrast to the noisy, sunlit world far above. Here, the darkness is absolute, a pervasive shadow that stretches endlessly in every direction. Within this boundless dark, occasional flashes of bioluminescence serve as fleeting, brilliant reminders of life. The temperature here hovers just above freezing, slowing down the metabolic rates of the creatures that navigate the dark. The ocean floor undulates in slow, muddy dunes, shaped by the gentle caress of deep-sea currents. Every movement in the abyss is deliberate, a conservation of precious energy in a world where food is scarce. Here, the darkness is absolute, a pervasive shadow that stretches endlessly in every direction. There is a profound stillness in these waters, a quiet that has remained unbroken for millions of years. Remarkably, despite centuries of observation, no adult eel has ever been observed spawning in the wild. Our knowledge of their spawning grounds is based largely on the discovery of their microscopic larvae in the Sargasso Sea. Genetic analysis has confirmed that all European and American eels originate from this single remote region. The eels arrive, spawn, and presumably die, leaving their offspring to drift back to coastal waters. It is a life cycle of immense proportion, tied inextricably to the unique conditions of this current-bound sea. The slow drift of water masses brings subtle shifts in chemistry, dictating the distribution of microscopic life. Here, the darkness is absolute, a pervasive shadow that stretches endlessly in every direction. This unseen world, though remote and alien, is fundamentally tied to the health and balance of the entire planet. The sheer volume of water overhead is incomprehensible, a liquid sky that presses down with unrelenting weight. The ancient rocks of the seafloor stand as silent witnesses to the slow, tectonic shifting of the Earth's crust. This is a realm where the frantic pace of the surface is forgotten, replaced by a slow, enduring rhythm. The immense pressure at these depths acts as a constant, invisible force, shaping the very biology of everything that dwells here. Within this boundless dark, occasional flashes of bioluminescence serve as fleeting, brilliant reminders of life. The chemical composition of these waters holds a subtle record of the ocean's vast, interconnected circulatory system. The immense pressure at these depths acts as a constant, invisible force, shaping the very biology of everything that dwells here. This unseen world, though remote and alien, is fundamentally tied to the health and balance of the entire planet. Each descending particle of organic matter carries a fraction of the surface's vitality down into the waiting abyss. The deep ocean is characterized by a prevailing cold and a scarcity of food, dictating the pace of life for its inhabitants. Deep-sea fish often exhibit remarkable longevity and extremely slow life histories. The orange roughy, known scientifically as Hoplostethus atlanticus, perfectly illustrates this deliberate approach to survival. These robust, deep-dwelling fish inhabit the cold waters around seamounts and continental slopes. They grow at an agonizingly slow rate, taking decades to reach sexual maturity. Every movement in the abyss is deliberate, a conservation of precious energy in a world where food is scarce. The immense pressure at these depths acts as a constant, invisible force, shaping the very biology of everything that dwells here. Life here moves at a glacial pace, a testament to the enduring patience required to inhabit the deep ocean. In this extreme environment, survival requires remarkable adaptations, biochemical miracles forged in the crushing deep. This unseen world, though remote and alien, is fundamentally tied to the health and balance of the entire planet. The deep ocean currents act as a global conveyor belt, distributing heat and nutrients in a slow planetary waltz. Each descending particle of organic matter carries a fraction of the surface's vitality down into the waiting abyss. The silence is vast and enveloping, offering a stark contrast to the noisy, sunlit world far above. Life here moves at a glacial pace, a testament to the enduring patience required to inhabit the deep ocean. The chemical composition of these waters holds a subtle record of the ocean's vast, interconnected circulatory system. This unseen world, though remote and alien, is fundamentally tied to the health and balance of the entire planet. The temperature here hovers just above freezing, slowing down the metabolic rates of the creatures that navigate the dark. Scientific studies of the otoliths, or ear bones, of the orange roughy have revealed staggering lifespans. Some individuals are estimated to live for more than 150 years. This extreme longevity is an adaptation to an environment where resources are unpredictable and reproduction may only be successful in certain years. A fish living for a century and a half has ample time to ensure the continuation of its lineage. However, this slow life history makes the species catastrophically vulnerable to modern pressures. This unseen world, though remote and alien, is fundamentally tied to the health and balance of the entire planet. The slow drift of water masses brings subtle shifts in chemistry, dictating the distribution of microscopic life. The steady accumulation of sediment slowly buries the past, layer upon microscopic layer, in the quiet depths. The chemical composition of these waters holds a subtle record of the ocean's vast, interconnected circulatory system. The temperature here hovers just above freezing, slowing down the metabolic rates of the creatures that navigate the dark. There is a profound stillness in these waters, a quiet that has remained unbroken for millions of years. The steady accumulation of sediment slowly buries the past, layer upon microscopic layer, in the quiet depths. The geological clock ticks softly in the deep, measuring time not in days or years, but in millennia and epochs. There is a profound stillness in these waters, a quiet that has remained unbroken for millions of years. The slow drift of water masses brings subtle shifts in chemistry, dictating the distribution of microscopic life. Life here moves at a glacial pace, a testament to the enduring patience required to inhabit the deep ocean. The steady accumulation of sediment slowly buries the past, layer upon microscopic layer, in the quiet depths. When commercial fishing operations discovered dense aggregations of orange roughy around seamounts, they were heavily exploited. The removal of large breeding adults decimated populations that had taken centuries to build. Because they mature so slowly, these populations cannot rapidly recover from intensive harvesting. The story of the orange roughy serves as a stark reminder of the mismatch between the pace of deep-sea biology and industrial exploitation. Managing these resources requires an understanding of timescales that far exceed typical human planning. The geological clock ticks softly in the deep, measuring time not in days or years, but in millennia and epochs. The deep ocean currents act as a global conveyor belt, distributing heat and nutrients in a slow, planetary waltz. The ocean floor undulates in slow, muddy dunes, shaped by the gentle caress of deep-sea currents. The slow drift of water masses brings subtle shifts in chemistry, dictating the distribution of microscopic life. Life here moves at a glacial pace, a testament to the enduring patience required to inhabit the deep ocean. The geological clock ticks softly in the deep, measuring time not in days or years, but in millennia and epochs. The ocean floor undulates in slow, muddy dunes, shaped by the gentle caress of deep-sea currents. This unseen world, though remote and alien, is fundamentally tied to the health and balance of the entire planet. The silence is vast and enveloping, offering a stark contrast to the noisy, sunlit world far above. The sheer volume of water overhead is incomprehensible, a liquid sky that presses down with unrelenting weight. The steady accumulation of sediment slowly buries the past, layer upon microscopic layer, in the quiet depths. Each descending particle of organic matter carries a fraction of the surface's vitality down into the waiting abyss. The realization that the deep ocean contains vast, uncatalogued biodiversity led to a monumental global effort. The Census of Marine Life, conducted between the years 2000 and 2010, sought to document this hidden world. Over 2,700 scientists from more than 80 countries collaborated on this unprecedented project. Their expeditions explored every ocean basin, from the sunlit surface to the deepest trenches. The census aimed to establish a baseline of marine biodiversity against which future changes could be measured. In this extreme environment, survival requires remarkable adaptations, biochemical miracles forged in the crushing deep. This is a realm where the frantic pace of the surface is forgotten, replaced by a slow, enduring rhythm. The deep ocean currents act as a global conveyor belt, distributing heat and nutrients in a slow, planetary waltz. Life here moves at a glacial pace, a testament to the enduring patience required to inhabit the deep ocean. This is a realm where the frantic pace of the surface is forgotten, replaced by a slow, enduring rhythm. The steady accumulation of sediment slowly buries the past, layer upon microscopic layer, in the quiet depths. There is a profound stillness in these waters, a quiet that has remained unbroken for millions of years. The sheer volume of water overhead is incomprehensible, a liquid sky that presses down with unrelenting weight. Here, the darkness is absolute, a pervasive shadow that stretches endlessly in every direction. Life here moves at a glacial pace, a testament to the enduring patience required to inhabit the deep ocean. There is a profound stillness in these waters, a quiet that has remained unbroken for millions of years. The sheer volume of water overhead is incomprehensible, a liquid sky that presses down with unrelenting weight. During this 10-year endeavor, scientists discovered an astonishing array of previously unknown organisms. They described over 6,000 potentially new species, many from the most remote and inaccessible regions of the sea. The census revolutionized our understanding of marine ecosystems and the intricate connections between them. It revealed that life in the ocean is far more diverse and resilient than previously imagined. The data collected continues to inform marine conservation efforts worldwide. There is a profound stillness in these waters, a quiet that has remained unbroken for millions of years. Life here moves at a glacial pace, a testament to the enduring patience required to inhabit the deep ocean. Within this boundless dark, occasional flashes of bioluminescence serve as fleeting, brilliant reminders of life. Here, the darkness is absolute, a pervasive shadow that stretches endlessly in every direction. This is a realm where the frantic pace of the surface is forgotten, replaced by a slow, enduring rhythm. The geological clock ticks softly in the deep, measuring time not in days or years, but in millennia and epochs. This unseen world, though remote and alien, is fundamentally tied to the health and balance of the entire planet. The chemical composition of these waters holds a subtle record of the ocean's vast, interconnected circulatory system. This is a realm where the frantic pace of the surface is forgotten, replaced by a slow, enduring rhythm. The silence is vast and enveloping, offering a stark contrast to the noisy, sunlit world far above. This unseen world, though remote and alien, is fundamentally tied to the health and balance of the entire planet. Here, the darkness is absolute, a pervasive shadow that stretches endlessly in every direction. Perhaps the most significant outcome of the census of marine life was a revised understanding of what remains to be found. The final estimate suggested that there are approximately 250,000 known marine species. However, the census also indicated that there are likely at least 750,000 species still undescribed. We share this planet with hundreds of thousands of life forms that we have yet to see or name. The vast majority of these unknown species reside in the deep ocean, hidden in the perpetual dark. The sheer volume of water overhead is incomprehensible, a liquid sky that presses down with unrelenting weight. The ocean floor undulates in slow, muddy dunes, shaped by the gentle caress of deep-sea currents. Each descending particle of organic matter carries a fraction of the surface's vitality down into the waiting abyss. Every movement in the abyss is deliberate, a conservation of precious energy in a world where food is scarce. The ocean floor undulates in slow, muddy dunes, shaped by the gentle caress of deep-sea currents. The silence is vast and enveloping, offering a stark contrast to the noisy, sunlit world far above. The sheer volume of water overhead is incomprehensible, a liquid sky that presses down with unrelenting weight. Life here moves at a glacial pace, a testament to the enduring patience required to inhabit the deep ocean. In this extreme environment, survival requires remarkable adaptations, biochemical miracles forged in the crushing deep. The ocean floor undulates in slow, muddy dunes, shaped by the gentle caress of deep sea currents. Life here moves at a glacial pace, a testament to the enduring patience required to inhabit the deep ocean. This unseen world, though remote and alien, is fundamentally tied to the health and balance of the entire planet. We return our focus to the gentle, unceasing descent of marine snow. This delicate biological rain connects the vibrant surface to the quiet depths, a slow transfer of energy and history. Each particle that settles on the abyssal plain contributes to an accumulating archive of planetary history. The sediment layers of the deep ocean form a vast, unbroken record of Earth's past. Millions of years of climate fluctuations, shifts in ocean circulation, and biological evolution are preserved in this soft mud. The chemical composition of these waters holds a subtle record of the ocean's vast, interconnected circulatory system. Life here moves at a glacial pace, a testament to the enduring patience required to inhabit the deep ocean. This is a realm where the frantic pace of the surface is forgotten, replaced by a slow, enduring rhythm. The ancient rocks of the seafloor stand as silent witnesses to the slow, tectonic shifting of the Earth's crust. Life here moves at a glacial pace, a testament to the enduring patience required to inhabit the deep ocean. The ocean floor undulates in slow, muddy dunes, shaped by the gentle caress of deep-sea currents. The chemical composition of these waters holds a subtle record of the ocean's vast, interconnected circulatory system. The silence is vast and enveloping, offering a stark contrast to the noisy, sunlit world far above. The chemical composition of these waters holds a subtle record of the ocean's vast, interconnected circulatory system. The slow drift of water masses brings subtle shifts in chemistry, dictating the distribution of microscopic life. The immense pressure at these depths acts as a constant, invisible force, shaping the very biology of everything that dwells here. Within this boundless dark, occasional flashes of bioluminescence serve as fleeting, brilliant reminders of life. By extracting long core samples from the seafloor, scientists can read this ancient archive. The microscopic shells of plankton trapped in the sediment provide clues about past temperatures and atmospheric conditions. The cyclical nature of ice ages is clearly documented in the alternating layers of specific marine organisms. Evidence of massive geological events, including major volcanic eruptions and even asteroid impacts, is embedded in the ocean floor. The deep ocean is the ultimate repository of planetary memory, holding the story of the Earth in its quiet, dark embrace. Life here moves at a glacial pace, a testament to the enduring patience required to inhabit the deep ocean. The chemical composition of these waters holds a subtle record of the ocean's vast, interconnected circulatory system. The ocean floor undulates in slow, muddy dunes, shaped by the gentle caress of deep sea currents. Here, the darkness is absolute, a pervasive shadow that stretches endlessly in every direction. The silence is vast and enveloping, offering a stark contrast to the noisy, sunlit world far above. The sheer volume of water overhead is incomprehensible, a liquid sky that presses down with unrelenting weight. The deep ocean currents act as a global conveyor belt, distributing heat and nutrients in a slow planetary waltz. This unseen world, though remote and alien, is fundamentally tied to the health and balance of the entire planet. The temperature here hovers just above freezing, slowing down the metabolic rates of the creatures that navigate the dark. The steady accumulation of sediment slowly buries the past, layer upon microscopic layer, in the quiet depths. The immense pressure at these depths acts as a constant, invisible force, shaping the very biology of everything that dwells here. Within this boundless dark, occasional flashes of bioluminescence serve as fleeting, brilliant reminders of life. When we consider the scale of the ocean, our terrestrial reference points often fail us. The deepest part of the ocean, the Mariana Trench, plunges to a depth of nearly 7 miles. To grasp this magnitude, we must imagine the highest peak on land, Mount Everest, placed into this trench. If Everest were resting on the bottom of the Challenger Deep, its summit would still be submerged under more than a mile of water. This staggering volume represents the largest habitable space on the planet, yet it is the least explored. In this extreme environment, survival requires remarkable adaptations, biochemical miracles forged in the crushing deep. Life here moves at a glacial pace, a testament to the enduring patience required to inhabit the deep ocean. The ancient rocks of the seafloor stand as silent witnesses to the slow, tectonic shifting of the Earth's crust. The sheer volume of water overhead is incomprehensible, a liquid sky that presses down with unrelenting weight. This is a realm where the frantic pace of the surface is forgotten, replaced by a slow, enduring rhythm. In this extreme environment, survival requires remarkable adaptations, biochemical miracles forged in the crushing deep. The ancient rocks of the seafloor stand as silent witnesses to the slow, tectonic shifting of the Earth's crust. The chemical composition of these waters holds a subtle record of the ocean's vast, interconnected circulatory system. The immense pressure at these depths acts as a constant, invisible force, shaping the very biology of everything that dwells here. There is a profound stillness in these waters, a quiet that has remained unbroken for millions of years. The temperature here hovers just above freezing, slowing down the metabolic rates of the creatures that navigate the dark. The deep ocean currents act as a global conveyor belt, distributing heat and nutrients in a slow planetary waltz. We are confronted with a slow meditation on the boundaries of our knowledge. There are entire ecosystems functioning in the deep sea that we have not yet observed. There are acoustic signals captured by deep ocean hydrophones that remain unidentified, the sounds of unseen giants or unknown physical processes. There are symbiotic relationships and biochemical adaptations that could revolutionize our understanding of biology. The ocean continues to guard its secrets with patience, revealing them only slowly to those who venture into the dark. Each descending particle of organic matter carries a fraction of the surface's vitality down into the waiting abyss. The steady accumulation of sediment slowly buries the past, layer upon microscopic layer, in the quiet depths. The silence is vast and enveloping, offering a stark contrast to the noisy, sunlit world far above. The sheer volume of water overhead is incomprehensible, a liquid sky that presses down with unrelenting weight. The silence is vast and enveloping, offering a stark contrast to the noisy, sunlit world far above. This is a realm where the frantic pace of the surface is forgotten, replaced by a slow, enduring rhythm. The immense pressure at these depths acts as a constant, invisible force, shaping the very biology of everything that dwells here. In this extreme environment, survival requires remarkable adaptations, biochemical miracles forged in the crushing deep. The silence is vast and enveloping, offering a stark contrast to the noisy, sunlit world far above. The sheer volume of water overhead is incomprehensible, a liquid sky that presses down with unrelenting weight. Let the weight of what we have learned settle as the journey concludes. The magnitude of the ocean, with its immense pressures and profound darkness, is not a void to be feared, but a sanctuary of quiet stability. We thank you for accompanying us on this exploration of the deep sea and its many enduring mysteries. The knowledge of this vast interconnected world can be carried lightly as you prepare to rest. The ocean will continue its slow, vital work while we sleep. It remains out there in the dark, still, ancient, and endlessly patient. Let the weight of what we have learned settle as the journey concludes. The magnitude of the ocean, with its immense pressures and profound darkness, is not a void to be feared, but a sanctuary of quiet stability. We thank you for accompanying us on this exploration of the deep sea and its many enduring mysteries. The knowledge of this vast interconnected world can be carried lightly as you prepare to rest. The ocean will continue its slow, vital work while we sleep. It remains out there in the dark, still, ancient, and endlessly patient.